Hello, and welcome back to Astronomy for Sleep, where the universe slows and the mind can rest among the stars. Tonight, let your thoughts drift gently beyond the day, past the clouds, past the quiet air, into a space where light itself was born. Before planets, before life, before even time as we know it, there were the stars, the great engines of creation, forging every element, every atom, every breath that would one day become us. In their hearts, gravity meets light. In their depths, the seeds of worlds are sown. Every sparkle you see in the night sky is both a beginning and an ending, a story written in fire, whispered across eons. So settle in, breathe slowly. Let the warmth of starlight fill the quiet between your thoughts. This is 101 Sleepy Facts About Stars, the engines of creation, a soft journey through the birth, life, and destiny of the lights that built the universe. Now let's begin. Stars begin in clouds of gas and dust called nebulae. If you could drift silently through the depths of space, far beyond the glittering constellations, you would eventually find yourself inside a vast, ghostly cloud. These regions, called nebulae, are not empty at all. They are oceans of hydrogen gas and fine cosmic dust, stretching for hundreds of light years. To our eyes, they appear as delicate veils of color when illuminated by nearby stars. But most of the time, they are dark, invisible against the black background of the cosmos. Inside these nebulae, the ingredients for creation wait patiently. Hydrogen, helium, carbon, oxygen, all the basic elements of matter, float there in silence, cold and motionless. Yet within that stillness, something begins to stir. Gravity, the universe's quiet sculptor, starts to weave its invisible threads, drawing atoms toward one another. And from that gentle pull, the first hints of a new star begin to form. Gravity slowly pulls these particles together. There is no rush in the language of the cosmos. Gravity moves slowly, almost meditatively. Over millions of years, small disturbances, perhaps the shock wave of a nearby supernova or the passing of another cloud, create ripples in the gas. Denser regions start to attract more material, their pull growing stronger as they gain mass. It's a cosmic feedback loop. The more matter they gather, the more irresistible their gravity becomes. Like raindrops merging in slow motion, particles drift inward, colliding softly, warming slightly, and continuing to fall toward an unseen center. The cloud begins to shrink, its vastness folding into itself. From the outside, it might look like nothing is happening at all. But deep within, the seeds of creation are gathering, drawn together by the same force that holds galaxies, planets, and even your feet to the ground. As the cloud collapses, it begins to spin. In the universe, motion is never entirely still. Even the quietest clouds carry a trace of rotation, a leftover swirl from the movements of their galactic home. As gravity pulls the cloud inward, that faint rotation speeds up, just as a figure skater spins faster when pulling in their arms. This spinning motion flattens the collapsing gas into a disk, a cosmic whirlpool of matter. At the center, pressure and heat increase. Around it, the flattened material begins to glow faintly. This rotation is not chaos. It's the beginning of order. The spinning prevents the entire cloud from collapsing instantly, allowing time for the core to grow dense enough to ignite. The universe, in its infinite patience, creates balance even in collapse. And so the future star begins to take shape, a warm heart forming within a spiraling cradle of dust. The center grows dense and hot, the seed of a star. At the heart of the spinning cloud, density builds until matter is packed tighter than anything found on Earth. The temperature soars to thousands, then millions of degrees. The pressure becomes unimaginable, crushing every atom together with tremendous force. This is the seed of a star, small compared to the original nebula, yet holding enough mass to light up worlds. In this growing core, the laws of physics prepare for transformation. Hydrogen atoms, usually content to float freely, are now trapped in a dance of collisions. Each impact raises the temperature a little more. The cloud's outer layers continue to fall inward, feeding the core. From this compression, a faint glow begins to appear, not from fusion yet, but from sheer heat. It is the warmth of birth, the fire before the flame. The darkness has begun to stir with light. This infant star is called a protostar. A protostar is not yet a true star, but it is alive in its own way, breathing heat, spinning steadily, still wrapped in the cocoon of its parent cloud. Around it, the disk of dust and gas continues to spiral, sometimes forming knots that may later become planets. The protostar grows brighter in infrared light, invisible to human eyes, but clear to telescopes like James Webb. Within, the battle between gravity and pressure intensifies. Gravity wants to crush it smaller. Internal heat pushes back. The result is a delicate balance, one that will determine whether this glowing seed becomes a stable star or fades into darkness. Each protostar is unique, shaped by the mass it gathers and the chaos around it. Some will ignite soon. Others will wait for millions of years, hidden from sight, dreaming in the quiet cradle of the nebula. Its temperature rises to millions of degrees. In the protostar's core, temperatures climb relentlessly. As more matter falls inward, the pressure at the center becomes extreme. At 10 million degrees, the atoms of hydrogen are stripped of their electrons, a sea of nuclei and particles colliding at incredible speeds. The heat is so great that light itself struggles to escape, trapped and scattered by dense plasma. Yet this energy builds, layer by layer, until the core begins to shimmer with the power of creation. The surface may still be shrouded by dust, but deep inside, the future star is preparing for ignition. Imagine the silence of space pierced by invisible heat. No sound, no flame, just an ocean of light waiting to be born. In these hidden furnaces, the destiny of entire worlds is being forged, silently, patiently, beautifully. When hydrogen atoms begin to fuse, the star is born. Then, one day, after millions of years of gathering, heating, and waiting, the threshold is crossed. The core becomes hot and dense enough for nuclear fusion to begin. Hydrogen nuclei, normally repelled by their identical charges, slam together with such force that they merge, forming helium. In that instant, mass transforms into energy, as described by Einstein's equation, E equals mc squared. This energy radiates outward, counteracting the pull of gravity. A perfect balance emerges. The star has found its heartbeat. Fusion will continue, steadily and serenely, for billions of years. What began as a dark cloud of gas has become a sun, shining across the universe. It is the moment of awakening, when darkness learns how to make light. Fusion releases energy, the light that reaches us. Every beam of starlight that touches your skin, every ray that glimmers in the ocean or warms a leaf, began as fusion energy deep in a stellar core. In those blazing hearts, hydrogen becomes helium, and the lost mass becomes light. The photons produced there take thousands of years to reach the star's surface, bouncing from particle to particle in a chaotic journey. Through plasma, when they finally escape, they travel across the vacuum of space, sometimes for billions of years, until they find a planet like ours. The light we see from the stars tonight began as fusion long before human history began. Every twinkle in the night sky is the universe's oldest form of communication, energy turned into beauty. The cosmos has been whispering through light since time began, and we, the observers, are its listeners. Every star you see was once part of a dark nebula. It's strange to think that the blazing jewels of the night sky were once invisible. Every star, even the brightest, was born from dust and shadow. The darkness that hides them is the same that gave them life. Within each glowing sphere lies the memory of a nebula, the quiet birthplace that condensed, collapsed, and transformed. Some nebulae still cradle newborn stars, glowing faintly as their children ignite within. Others have long since dispersed, their gases scattered back into space. Yet the pattern continues. Clouds become stars, stars die, and their ashes form new clouds again. The night sky is not static. It is an ongoing conversation between darkness and light, one giving birth to the other endlessly. The Orion Nebula still births stars today. If you look up toward Orion's belt on a winter night, just below it lies a soft patch of light, the Orion Nebula. It is one of the few stellar nurseries visible to the naked eye, glowing about 1,300 light-years away. Inside it, hundreds of stars are forming right now. Telescopes reveal pillars of gas and dust, illuminated by the newborn suns hidden within. Some are only a few thousand years old, cosmic infants compared to our 5-billion-year-old sun. The Orion Nebula is a reminder that creation is still ongoing. The universe has not stopped building, it simply moves at its own pace. To gaze at Orion is to look at the present moment of cosmic birth, light from the workshop of creation itself. Some stars form in clusters, siblings born together. Stars often come into existence not alone, but as part of a family. Within dense nebulae, many fragments collapse simultaneously, creating clusters of stars, cosmic siblings sharing the same origin. They drift together in groups of dozens, hundreds, sometimes thousands, bound by gravity. Over time, some remain close, forming open clusters like the Pleiades. Others scatter across the galaxy, their bond stretched by time. But their chemical fingerprints remain the same. Astronomers can trace their shared ancestry through starlight. Our sun may have once been part of such a cluster, long dispersed. Somewhere out there, its stellar siblings still shine, too far for us to see, yet forever connected by birth. Others drift alone in cosmic solitude. Not every star is born into companionship. Some form at the edges of clouds, isolated from others, destined to wander alone. These solitary stars travel the galaxy, with no companions to orbit or reflect their light. Yet in their solitude, they remain magnificent, carrying entire planetary systems, nurturing life, or shining for no one at all. Even in cosmic loneliness, there is purpose. A single star can light up a galaxy's corner, shaping its surroundings, influencing worlds that may never know they exist. Solitude, in space, is not emptiness. It is quiet persistence, a reminder that even alone, a single source of light can change everything around it. It can take millions of years for a star to ignite. The making of a star is a lesson in patience. From the first stirrings of gravity to the first flicker of fusion, millions, sometimes tens of millions, of years may pass. Nothing in nature rushes toward its destiny as slowly and gracefully as a forming star. To us, it seems stabilizes and finally ignites. It's a reminder that transformation often begins long before it is visible. The stars we see tonight began forming when early mammals were just starting to walk the Earth, or even before our planet existed at all. The sky is full of slow miracles. Gravity and radiation find a perfect balance. When a star finally awakens, it doesn't collapse or explode. It settles into equilibrium. Gravity pulls inward, radiation pushes outward. The two forces balance perfectly, holding the star in steady shape. This fragile harmony can last billions of years. It's a cosmic example of balance found through opposition, the same way day and night, motion and stillness, or life and death sustain each other. A star's peace is not the absence of struggle, but the equilibrium between competing forces. Every photon of light we see from the stars is the expression of that balance. Gravity made visible as radiance. That balance defines the stars. Lifetime. How long a star lives depends entirely on its mass. A massive star burns its fuel quickly, shining fiercely but briefly, millions of years at most. Smaller stars, like red dwarfs, sip their fuel slowly, glowing dimly for trillions of years. The universe is filled with both kinds, the short-lived brilliance and the eternal ember. Both are necessary. The giants create heavy elements in their violent deaths. The dwarfs provide stability and warmth for potential worlds. The life of a star, then, is not just about how long it shines, but what it gives back to the cosmos. During that time, the light of a star is gravity transformed into radiance. At its core, a star is a machine that turns gravity into light. Matter falls inward, fuses, and releases energy, A. Conversion so efficient that a single gram of hydrogen becomes enough light to power cities for centuries. This transformation links the physical with the poetic. The invisible pull of gravity becomes the visible gift of illumination. When you see a star's glow, you are witnessing gravity's patience rewarded, the universe's most elegant equation made visible. Light, in this sense, is not just energy. It is the physical expression of harmony between collapse and resistance, the balance that sustains creation itself. In a way, every sunrise on Earth began in a collapsing cloud. When sunlight pours through your window at dawn, it carries an ancient story. The atoms in that light were born billions of years ago, when the sun itself formed from a collapsing cloud of gas. That same process, gravity gathering, fusion igniting, has repeated across galaxies for eons. Every warm ray, every soft golden hue, is a continuation of that cosmic rhythm. The sunrise is not just a daily event. It is the echo of a process that began long before humanity existed. Each morning, the universe reminds us, creation is still ongoing, even in something as familiar as light. Even our sun was once part of a stellar nursery. Long before Earth existed, the sun was born inside a nebula, perhaps much like the Orion Nebula we see today. Around it swirled a disk of gas and dust that would eventually form the planets. Jupiter, Saturn, Earth, and all their moons began as grains in that glowing cradle. Nearby stars, siblings of our sun, have since drifted away, scattered by galactic tides. But their shared origin remains written in chemistry, a trace of the same molecular cloud that gave rise to our entire solar system. We are the descendants of a nebula, made from the same dust that once circled a newborn star. The universe keeps making new stars, though fewer than before. In the early universe, star formation was furious, galaxies blazed with newborn suns. But as cosmic gas was used up or locked inside aging stars, the rate began to slow. Today, stars are still being born, but less often. The universe is entering a quieter era, one of reflection rather than creation. Yet even this slower rhythm has beauty. It means that every new star is more precious, more deliberate, a final note in an ancient symphony. The cosmos is not ending. It is maturing, its fires burning more softly, its stories told more gently. Stars are time made visible. When we look at the stars, we are seeing time itself. Each point of light is an event from the past, some from a few years ago, others from billions. They are fossils of light, carrying ancient messages through the void. The universe, in this sense, has no present, only light in transit. Every star, every flicker, is a moment preserved, a record of creation written in brightness. To gaze at the night sky is to look into history, to witness the universe remembering itself. The stars are not just objects. They are time, glowing softly against eternity. Starlight carries information, like fingerprints across space. When you look at a star, you're not only seeing its glow, you're reading a message. Every photon that leaves a star's surface carries traces of its origin, a record of temperature, composition, and motion, encoded in color and pattern. Starlight is not uniform. It's full of subtle variations, tiny shifts in wavelength, gaps where certain colors are missing. These gaps are the fingerprints of atoms, the signature of elements that make up the star. Across the vast distances of space, light becomes a messenger more precise than sound or touch. Even though it may take millions of years to reach us, it still arrives intact, carrying its story in silent waves. When we study that light, we're not merely observing brightness. We're decoding the autobiography of the universe. Every element absorbs light at specific wavelengths. Imagine shining pure white light through a mist of atoms. Some wavelengths vanish, absorbed by the atom's electrons as they jump to higher energy levels. Each element removes a unique set of colors, creating a pattern of dark lines. Hydrogen leaves its mark, helium another, iron and calcium still others. No two elements share exactly the same pattern. It's as though each one speaks a private dialect in the language of light. These patterns, called absorption lines, are like cosmic barcodes. They allow scientists to identify the chemical makeup of a star from millions of light years away without ever touching it. The universe, it turns out, writes its secrets in light, and each element leaves its signature for those patient enough to learn how to read it. Astronomers use these lines to decode a star's chemistry. Through spectroscopy, astronomers pass starlight through a prism, separating it into its full rainbow of colors. When they examine the spectrum, they see the dark lines, the missing colors where specific elements have absorbed energy. By comparing these lines, present, and even in what proportions, it's as if a doctor could diagnose a distant patient by studying the tone of their voice carried on the wind. This method has revealed the composition of thousands of stars, nebulae, and galaxies. It has shown us that the same elements we find in our own bodies, hydrogen, carbon, oxygen, iron, also exist in the hearts of stars. We are made of the same material, illuminated by the same patterns of light. A star's color tells us its temperature. Color is more than beauty, it's a measurement. Blue stars blaze with fierce energy. Their surface is hotter than 25,000 degrees Celsius. Yellow stars, like our sun, are cooler, around 5,500 degrees. Red stars, dim and gentle, glow at only a few thousand degrees. This difference follows a simple law of physics. Hotter objects emit more light at shorter, bluer wavelengths. When you gaze at a star's color, you are actually sensing its temperature, feeling, across space and time, the heat of fusion deep in its core. Even the faintest red ember in the sky radiates ancient warmth, while a blue star burns with almost violent intensity. The colors of the night are not arbitrary. They are thermometers of the cosmos, written in the spectrum of creation. Blue stars are the hottest. They live fast and shine fiercely. In their cores, fusion proceeds at a furious rate, converting hydrogen into helium and heavier elements in only a few million years. Their light floods the surrounding space with ultraviolet radiation, sculpting nearby nebulae and igniting new waves of star formation. But their brilliance comes at a price. They die young, collapsing into supernovae long before smaller stars even mature. If you see a blue star, you are witnessing the universe in its most energetic and short-lived phase. Its glow is intense but fleeting, a cosmic firework in an otherwise timeless expanse. And when it dies, it leaves behind the raw materials for new worlds. Proof that even the brightest flames feed future light. Red stars are the coolest. They are the quiet ones, small, dim, and extraordinarily patient. Red dwarfs, which make up most of the stars in the Milky Way, burn their hydrogen so slowly that their lifespans stretch into the trillions of years. No red dwarf has ever died in the entire history of the universe. They simply haven't had time. Though faint to our eyes, these tiny suns are the most enduring beacons of creation. They shine softly, steadily, without drama. In their subdued light, planets may orbit peacefully for eons, sheltered from cosmic storms. While blue stars roar like giants, red stars whisper, their calm glow a symbol of cosmic endurance, the slow heartbeat of the galaxy. The sun, yellow-white, is a mid-range star. Our sun sits comfortably between extremes, neither too hot nor too cool, neither brief nor eternal. It belongs to the G-class stars, steady and balanced. Its golden light has bathed Earth for billions of years, nurturing oceans, life, and thought itself. In stellar terms, the sun is ordinary, one of countless similar stars scattered across the Milky Way. Yet to us, it is everything. Its color, a gentle yellow-white, reflects a perfect compromise of temperature and energy. It is bright enough to sustain life, but stable enough to endure. The sun reminds us that balance, not brilliance, is often the source of lasting harmony. In the quiet range between extremes, life finds its place. Light travels across billions of years to reach our eyes. Every time you look at the night sky, you are receiving ancient light. Some photons left their stars only a few years ago. Others began their journey before the Earth existed. They crossed the emptiness at 300,000 kilometers per second, slipping silently through space for eons. Along the way, they may pass planets, nebulae, and galaxies, yet continue unimpeded, carrying their message unaltered. When they finally reach Earth, they enter your eyes, completing a voyage of unimaginable duration. The light you see tonight might be older than humanity itself. To gaze upward is to experience time folded into a single moment, the past arriving as a gentle shimmer in the present. When we look at stars, we see the past. There is no now in astronomy. Light always takes time to travel, so even the nearest stars show us how they looked years ago. The farther we look, the deeper into the past we see. Some of the galaxies visible in powerful telescopes appear as they were billions of years ago, long before our sun had formed. In a sense, the universe is a time machine built of light. Every beam, every reflection, carries history embedded in its color and intensity. When you look up at night, you are not merely stargazing, you are time traveling. The night sky is not a picture of what is, but a portrait of what was, the visible memory of creation. Some of the light we see began before humans existed. Think of a photon that left its star 2 million years ago from the Andromeda galaxy. When it began its journey, early humans were just learning to use tools on Earth. That same particle of light has crossed intergalactic space ever since, untouched, unchanged, to arrive in your eyes tonight. It has survived cosmic dust, magnetic fields, and the expansion of space itself. And now, for a brief instant, it becomes part of your awareness before vanishing. In that moment, you share an intimate connection with an event that happened before humanity's story began. The light of the universe is ancient, but its arrival is always immediate, a reminder that every moment of seeing is also a meeting with eternity. Spectroscopy, reading starlight, revealed the universe's secrets. When scientists first spread starlight into its spectrum in the 19th century, they discovered something astonishing. The same patterns of lines appeared in laboratory experiments on Earth. The stars, it turned out, were not made of mysterious celestial matter. They were made of the same elements we find here. This realization shattered centuries of belief that the heavens were fundamentally different from the world below. The discovery of spectral lines connected heaven and earth through the laws of physics. It showed that the universe is one continuous whole, governed by the same rules everywhere. Every spectrum became a scientific poem, proof that nature speaks one language. Whether in a candle flame or a distant galaxy, it showed that hydrogen and helium dominate the cosmos. By carefully reading spectra, astronomers learned that almost 3/4 of the universe's visible matter is hydrogen, and most of the rest is helium. The heavy elements, carbon, oxygen, iron, are only traces forged later in the hearts of stars. This means that stars are both made of simplicity and creators of complexity. The two lightest elements serve as the foundation for everything else. Out of hydrogen and helium came all the materials for galaxies, planets, and life. The stars are the factories that turned that primal gas into diversity. Every breath you take began as hydrogen atoms in some ancient cloud, reassembled through the patience of stellar alchemy. It showed stars are suns, not distant fireflies. For much of human history, people saw stars as tiny lights scattered on a dome of night. Distant, cold, perhaps divine. But spectroscopy proved that stars are not mere points of light. They are suns, each blazing with nuclear fire like our own. They vary in size, color, and age, but their nature is the same. Every star you see is another sun, potentially with its own planets, its own sky, perhaps even its own watchers looking back. The realization expanded the human imagination beyond anything before. The sky was no longer decoration. It was a vast sea of suns, each a beacon of energy and possibility. It proved the universe obeys the same laws everywhere. The patterns of starlight are universal. Whether from a galaxy billions of light years away or a star near our sun, the same atomic transitions appear, the same physics applies. This consistency reveals something profound, that the universe is not random chaos, but an ordered system governed by shared principles. The same equations describe fusion in the sun and in distant galaxies. The same constants, speed of light, Planck's constant, gravitational force, apply everywhere. When astronomers realized this, they understood that science could truly describe the cosmos. The stars are not alien in kind. They are family, following the same natural rhythm as everything else that exists. Light shifts toward red as stars move away. When a star moves away from us, its light waves stretch slightly, increasing in wavelength. The color shifts toward the red end of the spectrum, a phenomenon known as the Doppler effect. You can hear a similar effect when a passing siren drops in pitch as it recedes. The same principle applies to light, though on cosmic scales. By measuring the amount of redshift, astronomers can tell how fast a star or galaxy is moving away. This small change in color is a map of motion, proof that even the seemingly still sky is in constant flow. Every redshifted photon is a subtle whisper of expansion. This redshift helped us discover cosmic expansion. In the early 20th century, Edwin Hubble measured the redshift of distant galaxies and found a remarkable pattern. The farther away a galaxy is, the faster it moves away from us. Space itself is stretching, carrying galaxies with it. This discovery became the foundation for modern cosmology, evidence that the universe began from a single, dense point and has been expanding ever since. Every redshifted ray of light is a clue to that story, a fossil record of motion written in color. Through these gentle shifts in starlight, we learn that the universe is not static but alive, growing, and still unfolding. Stars speak through photons. We listen with telescopes. No sound travels through space, but light carries all the conversation the universe needs. Every photon is a syllable, every wavelength a tone. Telescopes, our cosmic ears, gather these faint whispers and translate them into understanding. Radio telescopes listen to long, cool waves. Optical ones catch the visible glow. X-ray observatories tune into the most violent energies. Together, they let us hear the full symphony of the cosmos, from the calm hum of hydrogen to the roar of colliding galaxies. Stars speak constantly, and all we need to do is listen in the right way. Science, in its quietest form, is simply the art of listening to light. The night sky is a silent language of light. Above us, billions of stars communicate in a code of brightness and color. They speak not in words, but in wavelengths. Each glimmer is a phrase, each hue, a tone in the grand cosmic sentence. From the surface of the earth, the sky appears still, yet it is full of ongoing dialogue, stars aging, colliding, dimming, being born. We live under a constant stream of light-based messages, many of which began before life existed here. To watch the night sky is to witness an infinite conversation carried on without sound, a pure form of expression where silence and brilliance become one. Each star is both a messenger and a mystery. Starlight reveals much, yet never everything. It tells us about temperature, motion, and composition, but not about meaning. We can read the physical facts, but their beauty remains wordless. A star may be a sun with planets or a dying ember. We cannot always tell. Yet perhaps that's what keeps us looking, that blend of knowledge and wonder, the way mystery survives even under understanding. Each photon carries data, but also awe. Science can translate one, but not the other. So we keep gazing, balancing knowing and not knowing. Letting light teach us, but also leave us silent. To study light is to study time itself. Light is not just illumination, it is history in motion. Every photon is a record of when and where it began, traveling unaltered across billions of years. When we collect light from the cosmos, we are reading the universe's diary, one page at a time. In studying light, we study the unfolding of time, how the past becomes visible in the present, how energy weaves itself into memory. The universe does not keep time with clocks, it keeps time with light. And every starlit night is an invitation to read those glowing pages, to rest beneath eternity and feel, for a moment, part of its luminous story. Stars come in many kinds, classified by their spectra. At first glance, the stars all seem alike, distant points of white light scattered across the sky. But through a spectroscope, their differences unfold. Some shine with cool red warmth, others with blue-white intensity. Each star emits light across a range of wavelengths, and the pattern of that light forms a spectrum, a unique fingerprint that tells astronomers its temperature, composition, and stage of life. These patterns became the basis for the stellar classification system. What seems to us like a uniform sky is in truth a vast community of individuals, each star carrying its own traits, its own destiny. They differ in mass, in age, in brightness, but all belong to the same cosmic family, born of hydrogen, shaped by gravity, and fueled by fusion. The main sequence spans from blue giants to red dwarfs. If you were to plot all known stars on a graph of temperature versus brightness, most of them would fall along a single sweeping band, the main sequence. Here lie stars in their prime, steadily fusing hydrogen into helium. At the upper left of the sequence are the hot, massive blue giants. At the lower right, the cool, dim red dwarfs. The sun rests comfortably in the middle. This diagram, known as the Hertzsprung-Russell diagram, is one of astronomy's great maps, a portrait of stellar evolution in a single curve. It shows that stars are not random, but organized by physical laws, their positions determined by mass and heat. From brilliant giants to quiet dwarfs, all are stages of the same grand process, the steady burning of time into light. OBAF GKM, the classic stellar order. Astronomers developed a shorthand to classify stars by temperature and color. O, B, A, F, G, K, M, from hottest to coolest. O-type stars blaze blue, with temperatures above 30,000 degrees Celsius. M-type stars glow red, just a few thousand degrees. Between them lie all the varieties of stellar heat. A simple mnemonic, "Oh, be a fine girl/guy, kiss me," has helped generations of astronomers remember the sequence. Our Sun, a G-type star, sits near the middle, balanced between extremes. This scale reminds us that even in the vastness of space, patterns emerge. The universe, for all its complexity, obeys order. The letters may seem arbitrary, but behind them lies the physics of fusion, the art of temperature, and the subtle palette of cosmic color. O-type stars burn fast and die young. Among the stellar hierarchy, O-type stars are the titans, massive, brilliant, and fierce. They radiate more light in a single day than our Sun emits in a year. But such power comes at a cost. Their enormous gravity compresses their cores, driving fusion at a relentless pace. In just a few million years, a blink in cosmic time, they exhaust their hydrogen, swell, and collapse in violent supernovae. Their deaths seed space with heavy elements, enriching the galaxy for future generations of stars and planets. Though brief, their lives are transformative. They are the fireworks of creation, short-lived, dazzling, and forever altering the universe around them. M-type stars burn slowly and live trillions of years. At the other extreme are the small, cool, and patient M-type stars, the red dwarfs. They burn their hydrogen so efficiently that they can shine for trillions of years, outlasting every other kind of star. None have yet died. The universe itself isn't old enough for that. Their faint, ruby light may seem humble, but their longevity gives them power of a different kind, endurance. Around many of these red dwarfs, planets orbit quietly, warm just enough for the possibility of life. While blue stars live like comets, bright and brief, red dwarfs live like embers, glowing endlessly in the dark. In their slow fire, the universe practices eternity. Our Sun is a G-type star, balanced between the brilliance of blue giants and the patience of red dwarfs. Our Sun represents the middle path, steady, warm, and enduring. With a surface temperature around 5,500 degrees Celsius, it fuses hydrogen calmly, maintaining equilibrium for billions of years. Its stability makes life possible. Its rhythm governs every heartbeat on Earth. The Sun's classification, G2V, means it's a main sequence star of moderate heat and size. Ordinary among stars, yet extraordinary. In its influence, it reminds us that balance is its own kind of brilliance. The Sun does not seek to burn too fast or too slow. It simply endures, quietly sustaining a world that once looked up and named it life. Red dwarfs are the most common in the Milky Way. If you could count every star in our galaxy, you'd find that most are not like the Sun. The vast majority, about 3 out of every 4, are red dwarfs. They are small, cool, and faint, invisible to the naked eye yet dominating in number. The Milky Way glows not because of a few bright stars, but because of countless dim ones. These tiny suns form the hidden backbone of the galaxy, quietly burning hydrogen in near-infinite patience. Some host planets that may orbit so closely they complete a year in days. Others drift alone in silence. Their light may be weak, but their abundance makes them the quiet majority of the cosmos. Unseen, but essential. Blue giants shine 1,000,000 times brighter than the Sun. To see a blue giant is to witness power at its most extravagant. These immense stars, many times the mass of our Sun, blaze with unimaginable intensity. Their ultraviolet radiation can ionize entire nebulae, making them glow in spectacular colors. Yet their brightness comes at the cost of brevity. A blue giant may live only a few million years before collapsing in spectacular fashion. Their deaths create neutron stars, black holes, and the heavy elements that enrich future galaxies. In their short lives, they pour out energy enough to light the universe, a reminder that brilliance and impermanence often walk hand in hand. Brown dwarfs are failed stars, too small to ignite. Between the largest planets and the smallest stars lies a twilight category, the brown dwarfs. They form like stars, collapsing from clouds of gas, but never gain enough mass to trigger sustained fusion. Their cores glow faintly with leftover heat from contraction, radiating dimly in infrared light. Too big to be planets, too small to be stars. They are the cosmic in-betweens, the quiet failures of creation, or perhaps its humble experiments. Brown dwarfs show that the line between starlight and darkness is not sharp, but gradual. Even in failure, the universe produces beauty, soft, hidden, and glowing with quiet persistence. Binary systems are common, two stars orbiting one another. Most stars are not alone. They come in pairs, locked together by gravity, circling a common center of mass. Some binaries are close enough that their outer layers touch, exchanging matter in a slow celestial dance. Others orbit so far apart that it takes centuries to complete one revolution. These systems reveal the complexity of stellar relationships. One star may age faster, expanding and shedding material onto its companion. Sometimes, this exchange triggers nova outbursts, brief flashes of renewed brightness. The universe loves pairs, echoes of balance, attraction, and shared destiny, repeated from atoms to galaxies. Triple and quadruple systems also exist. Beyond pairs, some stars live in groups of 3, 4, or more, intricate gravitational ballets that defy simplicity. In such systems, the orbits can be unstable, with stars exchanging partners or swinging close before drifting apart again. Yet many remain stable for billions of years, moving in elegant harmony. To observe them is to witness the poetry of gravity, an invisible geometry that arranges chaos into dance. These multi-star systems show that the cosmos. Some expand and contract rhythmically, their brightness rising and falling in repeating cycles. These are variable stars, celestial heartbeats visible across the galaxy. Their pulsations can be caused by internal instabilities or by eclipses in binary systems. To ancient observers, their flickering was mysterious, perhaps divine. To modern astronomers, it's a key to understanding stellar structure. The rhythm of their light carries clues about density, temperature, and distance. Like breathing, it reminds us that even stars live in motion, expanding, contracting, shimmering with quiet rhythm in the dark. Cepheid variables help measure cosmic distances. Among variable stars, Cepheids hold special importance. Their brightness changes in a predictable way. The longer their period of pulsation, the more luminous they are. By measuring the time between peaks of brightness, astronomers can determine a Cepheid's true luminosity and thus its distance. This discovery, made by Henrietta Swan Leavitt in the early 1900s, transformed astronomy. Cepheids became cosmic yardsticks, allowing us to measure the scale of the universe. Through their gentle flicker, humanity first grasped how vast creation truly is. Their pulse is not just light. It is the beat of discovery itself. Neutron stars are the densest matter we know. When massive stars explode as supernovae, their cores collapse under gravity to form neutron stars, city-sized objects with the mass of the sun. In these remnants, atoms are crushed so tightly that protons and electrons fuse into neutrons, forming matter so dense that a teaspoon would weigh billions of tons. Some neutron stars spin rapidly, emitting beams of radiation that sweep through space like lighthouse beams. We call them pulsars. They are the remnants of death and yet still shine, their rotation echoing the heartbeat of the cosmos. They remind us that even after destruction, energy finds new ways to speak. White dwarfs are stars in quiet retirement. When a medium-sized star like our Sun exhausts its fuel, it sheds its outer layers, leaving behind a dense core, a white dwarf, about the size of Earth. But with half the Sun's mass, it glows with residual heat for billions of years, slowly cooling into darkness. These stars no longer fuse elements. They simply radiate the leftover warmth of their former brilliance. In their stillness lies dignity, a quiet end after a long and luminous life. White dwarfs are cosmic embers, reminders that even in fading light, there is beauty and peace. Supergiants swell before collapsing. In their final acts, the most massive stars swell into supergiants. Immense orbs thousands of times the size of the sun. Betelgeuse, for example, is so vast that if placed at the center of our solar system, it would extend beyond Jupiter. Inside, complex fusion reactions build heavier and heavier elements, forming layers like an onion. But once iron appears in the core, fusion can no longer release energy. The balance breaks. Gravity takes over, and within seconds, the core collapses, triggering a supernova explosion that outshines entire galaxies. From that violent end, the cycle of creation continues, matter scattered, ready to form new stars again. Every star's color is a story about its age and mass. Color is not just temperature, it is biography. A young, massive star glows blue, radiant with youth and energy. As it ages, it cools and reddens, drifting down the main sequence toward gentler hues. Lower mass stars begin red and stay that way for trillions of years, barely changing at all. Through color, the universe tells the story of time, a chromatic record of birth, maturity, and decline. To study the colors of stars is to read their life histories written in light. The night sky is not random decoration. It is an archive of stellar evolution, painted across eternity in shades of fire. Even in their differences, all stars share one process: fusion. Whether they are blue giants or red dwarfs, white dwarfs or neutron remnants, all stars trace their ancestry to one universal mechanism: nuclear fusion. It is the process that transforms gravity's pressure into energy, turning matter into light. Fusion unites every star under a single law of physics, the same reaction that powers our sun also fuels the distant stars of other galaxies. It is the universal heartbeat of the cosmos. Through fusion, the universe learned how to shine, and through its steady rhythm, everything that exists, planets, elements, life, was made possible. Stars evolve, just like living beings. Though they seem eternal, stars are not fixed. They are born, mature, and eventually die. They change in color, brightness, and size, passing through predictable stages of evolution. Some expand into giants, others shrink into dwarfs. Their lives are governed by mass, their destiny written in their weight. The heaviest burn fast and end violently. The lightest burn gently and last almost forever. In their life cycles, we glimpse our own beginnings, transformations, endings, and the continuation of matter beyond. The stars are not only physical phenomena, they are reflections of life itself, repeating the same cosmic rhythm on a grand scale. They are the atoms of galaxies. Every galaxy, no matter how vast, is made of stars. Each one is like an atom in a greater organism, bound together by gravity, forming the luminous fabric of the cosmos. From there, collective light, galaxies take shape, spirals, ellipses, clusters shimmering in the dark. The stars give galaxies their structure, their color, their evolution. When stars are born, galaxies grow brighter. When they die, galaxies dim. Just as atoms compose your body, stars compose the body of the universe. To look at the Milky Way is to see the sum of its countless stellar lives. The galaxy breathing, glowing, evolving, one star at a time. Fusion is what powers every star. At the core of every shining point in the sky lies a single, universal process, fusion. It is the quiet miracle that transforms darkness into light, matter into energy, stillness into radiance. Without fusion, there would be no stars, no warmth, no galaxies, not even atoms beyond. Hydrogen. It is the cosmic engine that keeps time itself unfolding. Inside a star's heart, unimaginable pressures bring atomic nuclei so close together that they merge. Each union releases a spark of energy, and those sparks, multiplied 1,000,000,000,000 times a second, create the glow that fills the universe. Every sunrise, every reflected shimmer on the ocean, every flicker in the night sky, all are born from fusion's invisible fire. It is the pulse of existence itself, beating softly in every star that ever was. In the sun, hydrogen fuses into helium. Our own sun is a vast fusion reactor. Silent, steady, perfectly balanced. Deep within its core, at 15 million degrees, hydrogen atoms collide and merge to form helium. Each fusion reaction releases energy in the form of gamma rays, which scatter outward, gradually losing energy until they emerge as the sunlight that touches your face. This transformation is simple in principle, yet profound in consequence. The light that powers. Life on Earth began as atomic unions billions of kilometers beneath the sun's surface. Every second, the sun renews this process endlessly. The same rhythm that began long before life existed and will continue long after we are gone. For hydrogen, nuclei merge to form one helium nucleus. The simplest element in the universe, hydrogen, is also its most powerful fuel. In the intense heat and pressure of a star's core, for hydrogen nuclei, protons, collide and combine through a chain of reactions to form a single helium nucleus. The new nucleus weighs slightly less than the sum of its parts. That tiny loss of mass is not gone. It has become energy, following Einstein's elegant equation, E equals mc squared. That energy radiates outward, creating the light and warmth that define a star. In every fusion reaction, the universe rewrites matter into energy, and energy into beauty. The missing mass becomes pure energy, light. This is the heart of Einstein's revelation. Matter and energy are two sides of the same reality. When fusion occurs, a fraction of matter is transformed into pure light. Photons that race outward at the speed of time. Those photons begin a long, wandering journey through the dense interior of the star, bouncing and scattering for thousands of years before finally escaping into space. When they reach Earth, they illuminate oceans, clouds, and eyes. The light that allows us to see the world is ancient, born from matter that gave itself up to become energy. Every glimmer you witness is the memory of matter transformed into light. Every second, the sun converts 600 million tons of hydrogen. In the quiet of space, the sun burns with inconceivable efficiency. Every second, it fuses roughly 600 million tons of hydrogen into helium. Yet the energy released sustains not only its own brilliance, but the entire solar system. Of that mass, about 4 million tons vanish entirely, converted into light and radiation. To us, it seems constant and serene. But beneath its surface is a storm of nuclear reactions, ceaseless and precise. Despite this staggering consumption, the sun is far from exhaustion. It has been burning for billions of years, and billions more remain. Its steady sacrifice is the reason we exist, a continuous act of creation written in fire. Yet it has enough fuel for billions of years. The scale of a star's energy supply defies imagination. The sun, halfway through its lifespan, has already shone for 4.6 billion years and will continue for about the same again. Its hydrogen reserves are vast, and fusion is astonishingly efficient. Only a small fraction of the sun's total mass is needed to sustain its radiance for eons. Each second of sunlight that touches our planet is part of a long, measured rhythm, one that will outlast every mountain, civilization, and memory. Stars, in their patience, remind us that endurance is a form of grace. Their fires burn not with haste, but with cosmic calm. Fusion happens in the star's core. At the very center of every star lies a region where conditions are extreme enough for fusion to occur. Temperatures soar into the millions. Pressures are so immense that atoms are crushed together against their mutual repulsion. This inner furnace is small compared to the star's total size. Yet it holds all the power. Surrounding layers conduct and transport the energy outward, through radiation and convection, until it reaches the surface. The star's brilliance is merely the outer reflection of what happens in this deep, hidden core. The visible light we see is the gentle echo of a violent, ordered chaos, the quiet miracle at the heart of every sun. The balance between gravity and pressure keeps it stable. Stars live in a perfect tension between two opposing forces. Gravity pulls inward, trying to crush the star into itself. Fusion pushes outward, releasing energy that resists collapse. When these two forces balance, the star becomes stable, neither shrinking nor expanding. This equilibrium can last billions of years. It's the universe's most exquisite balancing act. Destruction and creation, compression and release, held in eternal harmony. If gravity wins, the star collapses into a white dwarf or black hole. If fusion overpowers, it swells into a giant and dies. But for most of its life, a star remains poised between the two, glowing serenely, a symbol of balance achieved through opposition. Without fusion, a star collapses. When a star exhausts its nuclear fuel, its core loses the energy that once pushed outward against gravity. There is nothing left to counter the inward pull, and the core begins to shrink. As it contracts, it heats up, sometimes igniting new layers of fusion temporarily, but eventually, even those fade. The star's outer layers fall inward or are blown away in violent eruptions. Without fusion, the heart of the star implodes, often leaving behind a white dwarf, a neutron star, or even a black hole. Death, in the life of a star, is simply the moment when balance can no longer be maintained. The same force that gave it shape reclaims it. Without gravity, it explodes. If gravity were suddenly removed, a star's fusion would tear it apart instantly. The outward pressure of its internal reactions is enormous, and only gravity's steady hand keeps it contained. The universe itself depends on this constant tension, a dialogue between pull and push, contraction and release. Gravity is not the enemy of light. It is its sculptor. Without it, fusion would have no form, no rhythm, no meaning. The existence of stars and of life depends on this duality. Creation always needs containment. Energy always needs a center. Gravity gives light its home. Heavier stars fuse heavier elements, up to iron. As stars age, their cores grow hotter, and fusion begins to forge heavier and heavier elements. Hydrogen becomes helium. Helium becomes carbon and oxygen. Carbon becomes neon, magnesium, silicon, and finally, iron. Each new stage occurs faster than the last, as the star's life accelerates toward its end. But when iron appears, something profound happens. Fusion stops yielding energy. Iron resists transformation. The star can know longer sustain its outward pressure, and collapse becomes inevitable. Yet from that impending death comes creation, the violent supernova that will scatter all those elements into space, seeding the next generation of stars and worlds. Beyond iron, fusion costs energy instead of giving it. Iron marks the boundary between giving and taking, the end of a star's creative phase. Fusing elements heavier than iron consumes energy rather than releasing it. When a massive star's core fills with iron, fusion halts, and gravity surges unchecked. In a heartbeat, the core collapses. Temperatures spike to unimaginable levels, and the star's outer layers explode outward in a supernova. In that fleeting, cataclysmic moment, the heavier elements, gold, uranium, platinum, are forged. The star dies, but the universe grows richer. From the stillness of iron to the brilliance of explosion, creation and destruction merge into one act. That limit is the beginning of a star's end. Every star carries its own end within it, encoded in its mass. For the most massive, that end arrives swiftly. Once iron builds up, collapse is unstoppable. The heart falls inward. The outer layers rebound, and the star tears itself apart. For smaller stars, the decline is gentler, but the principle is the same. The moment fusion falters, gravity takes control. The universe does not waste. Every ending feeds another beginning. The material cast off by dying stars becomes the dust and gas from which new ones are born. Even in death, the process continues. Infinite and circular, like breathing on a cosmic scale. Fusion created the carbon in your body. Every atom of carbon in your body, in your skin, your bones, your thoughts, was once forged in the core of a long-dead star. In that ancient furnace, helium fused into carbon through the triple alpha process, where 3 helium nuclei combined to form one carbon atom. When that star died, it released its contents into space, scattering the elements that would later form planets, oceans, and life. The carbon that lets you breathe, move, and think is not native to Earth. It is stardust, recycled through time. You are, quite literally, a child of fusion, the living continuation of a process that began billions of years before you were born. It made the calcium in your bones. The calcium that gives your body strength was once inside a star, fused from lighter elements in a shell of nuclear fire. When that star reached the end of its life, it cast those atoms outward, mixing them into the clouds that would one day form our solar system. Each bone you move carries the memory of a star's death, not in tragedy, but in transformation. The firm structure of your body is, in essence, crystallized starlight. Fusion is not only the reason stars shine, it is the reason we stand, move, and exist. The solidity of matter is born from the impermanence of stars. The gold in your ring was forged in a dying star. Gold, that symbol of permanence and beauty, was born in violence. It formed not in gentle fusion, but in the explosive chaos of a supernova or the collision of neutron stars. In those final moments, the density and temperature become so extreme that atomic nuclei capture neutrons in rapid succession, creating the heaviest elements known, gold. Among them, these atoms scattered across the galaxy, drifting for billions of years before becoming part of our world. The gold you wear today is a relic of stellar death, the frozen light of an ancient explosion, transformed by time into something enduring and human. Fusion is the universe's alchemy. Long before humans dreamed of turning lead into gold, the universe had already mastered transmutation. Fusion is the original alchemy, the transformation of one element into another through the heat of creation. It turns the simplest matter into the building blocks of complexity. Hydrogen becomes helium, helium becomes carbon, and from there, the ladder of elements unfolds. Everything tangible, from mountain stones to human hearts, traces back to this process. The stars are the universe's laboratories, where matter learns how to evolve. Alchemy, once a dream of mystics, is reality written into the physics of light. Every atom of life is stardust, rearranged. We are not separate from the stars. We are their continuation. Every atom of oxygen in your lungs, every iron atom in your blood, was once part of a star that lived, burned, and died long before Earth existed. Over billions of years, those atoms traveled through space, joined into clouds, became planets, and eventually, life. When you breathe, you exchange elements, forged in ancient suns. When you look at the stars, you are looking into a mirror, one made of time, energy, and matter that has always been the same. Life is the universe learning to see itself. Through stardust eyes, the universe breathes through stars. Stars are not static. They are the lungs of the cosmos. They inhale raw hydrogen and exhale the elements of complexity. Their birth enriches galaxies. Their death returns matter to the void, ready to be reborn. This cycle of creation and destruction, inhalation and exhalation, gives the universe rhythm. Through stars, space becomes alive, dynamic, evolving. Every flicker of light you see is a breath in that endless respiration. And when a star dies, it is not a silence but a sigh, the universe releasing what it no longer needs so that something new can begin. Their heat is the heartbeat of creation. The warmth of the stars is more than temperature. It is the pulse of existence. Without it, the universe would be dark, sterile, and cold. Fusion's heat flows outward, warming planets, driving weather, igniting chemistry, and awakening life. That same heat is the energy of transformation, the bridge between physics and consciousness. When we feel the sun's warmth, we are sensing the heartbeat of creation itself, the ancient rhythm that has pulsed since the first stars ignited. The cosmos does not beat with sound but with light, with energy, with the constant, steady thrum of fusion, the eternal heart of everything that is. Our sun formed about 4.6 billion years ago. Long before the Earth cooled, before oceans or sky existed, the sun was born from a cloud of gas and dust swirling in the young Milky Way. That cloud collapsed under gravity's pull, spinning faster as it shrank, until its center grew hot enough to ignite fusion. Around the newborn star, the leftover material flattened into a disk, the seabed of planets. In that quiet dawn of the solar system, our sun began to shine, a steady flame in a dark, chaotic cosmos. 4.5 billion years later, it still burns with the same patient light, the same rhythm that has watched continents drift, species rise, and oceans breathe. The sun's age is written not only in rocks and craters, but in every heartbeat warmed by its glow. It was born from the same cloud as the planets. The sun and its family share a single origin, a vast molecular cloud rich with hydrogen, helium, and traces of heavier dust from older stars. As the sun formed at the center, the remaining material swirled around it, clumping into smaller bodies. Those clumps became planets, moons, asteroids, and comets. Every grain of sand on Earth, every drop of water, every molecule of air, once orbited as dust around the same newborn star. The solar system is a family bound not by coincidence, but by shared birth, one event, one cloud, one spark of creation that divided itself into star and worlds. The early sun was more active, flaring often. In its youth, the sun was a restless child. Its surface boiled with magnetic storms, and giant flares erupted frequently, flinging charged particles far into space. These tempests were hundreds of times more powerful than those we see today. Early Earth, still forming its crust and atmosphere, endured a constant bombardment of solar wind. Yet paradoxically, this violence may have helped spark the chemistry of life. energizing molecules, shaping weather, and driving the evolution of early atmospheres. Even chaos can nurture creation. The sun's youthful fury carved the conditions for calm that would follow. Its light shaped Earth's atmosphere. Without the sun's radiation, Earth's air would never have evolved into the delicate balance we breathe today. Ultraviolet light split molecules in the upper atmosphere, allowing oxygen to accumulate and ozone to form, a shield against the very energy that created it. Over billions of years, the sun's steady warmth stabilized our climate, turning a once hostile world into a cradle for oceans, plants, and eventually thought. Every cloud, every wind current, every flicker of dawn is orchestrated by solar energy. The sun is not just distant light. It is the sculptor of weather, color, and the fragile equilibrium we call home. The sun holds 99.8% of the solar system's mass. Almost everything that makes up our planetary system, from Mercury to Neptune, from icy comets to drifting dust, exists because the sun commands it. Its gravity holds 99.8% of all the system's mass, anchoring every orbit and shaping every path. Even Jupiter, immense as it seems, is only a faint echo of the sun's power. The solar system is, in essence, the sun's gravitational field made visible. Planets are simply ripples in its dominion. When you look up at the sky, remember, the sun is not at the center of our system by chance. It is the system. Its magnetic field drives solar winds. Flowing outward from the sun is a continuous stream of charged particles, electrons and protons racing through space at hundreds of kilometers per second. This flow, known as the solar wind, arises from the sun's magnetic field twisting and snapping above its surface. The wind extends far beyond Pluto, creating a vast bubble called the heliosphere, which shields the planets from much of the galaxy's radiation. Every gust of solar wind is magnetic music, invisible yet immense, shaping auroras on Earth and sculpting the tails of comets. The sun breathes magnetism. Space responds with shimmering light. Those winds sculpt comet tails. When a comet ventures near the sun, heat releases gas and dust from its icy nucleus. The solar wind catches these particles and sweeps them outward, forming the comet's luminous tail. The tail always points away from the sun, even as the comet moves, a constant reminder of the star's unseen breath. Through telescopes, we see these glowing trails as elegant signatures across the sky, delicate and temporary. Each one is a painting made by sunlight and wind, proof that even at great distance, the sun's influence is artistic as well as physical, a fusion of gravity, motion, and beauty. The sun's light takes 8 minutes to reach Earth. Though light travels at the fastest speed possible, 300,000 kilometers per second, the distance between the sun and Earth is so vast that sunlight takes about 8 minutes and 20 seconds to arrive. That means every sunrise is already 8 minutes old. The warmth you feel, the colors you see, are memories of energy that left the sun moments ago. On cosmic scales, that delay is tiny. Yet it reminds us that we live in the past of our own star. Even the sun, the photosphere, glows at roughly 500 degrees Celsius. Here, photons finally escape after their long journey from the core, radiating outward in every direction. To the naked eye, this region seems smooth and golden, but through high-resolution telescopes, it's alive with granules, convection cells the size of continents, constantly rising and sinking. The photosphere is the sun's skin, restless yet steady, the boundary between internal fire and the darkness of space. Its light defines the color of day, and its temperature sets the rhythm of life below. The core burns at 15 million degrees Celsius. Deep inside, where gravity is strongest, lies the fusion furnace. Hydrogen atoms collide fast enough to overcome their mutual repulsion and fuse into helium, releasing energy that sustains the sun's glow. The photons born there may take hundreds of thousands of years to work their way to the surface. When they finally escape, they cross space in minutes to touch our world. Every warm breeze, every sprouting seed, carries the imprint of those ancient photons. Energy born in the heart of a star and released into the poetry of life. The sun rotates once every 27 days. Though it appears motionless in the sky, the sun slowly turns on its axis. At the equator, one rotation takes about 27 days. Near the poles, it's slower. This differential rotation twists the sun's magnetic field, storing tension that eventually bursts as flares and sunspots. Over an 11-year cycle, its magnetism waxes and wanes, echoing in patterns of light across the solar system. The sun's slow spin is like the ticking of a vast clock, marking cosmic time. In magnetic rhythms, unseen yet essential, its rotation connects every pulse of space, weather to the steady choreography of stellar motion. Sunspots mark magnetic storms. Dark patches sometimes appear on the solar surface, sunspots. They are cooler regions, thousands of degrees lower than their surroundings, created by intense magnetic fields that inhibit convection. Though darker, they are still brighter than any earthly fire. Their appearance follows the sun's magnetic cycle, growing in number during periods of heightened activity. When clustered, they can herald powerful eruptions that send waves of energy toward Earth. To ancient sky watchers, these spots were blemishes on perfection. To scientists, they are clues to the sun's inner workings, magnetic footprints left upon a sea of fire. Solar flares release immense energy bursts. At times, magnetic tension on the sun's surface snaps, releasing energy equivalent to millions of hydrogen bombs in seconds. These are solar flares, explosions of light, radiation, and particles that surge outward at near light speeds. They illuminate the sun's corona and send shockwaves through the solar system. While the Earth's magnetic field shields us from most of their effects, satellites and astronauts must take caution. Auroras shimmer brighter, communications can falter, and space itself ripples with the afterglow of the sun's brief fury. Even in peace, our star remembers how to roar. These can disturb satellites and power grids. When charged particles from solar flares reach Earth, they interact with our magnetic field, inducing electric currents in the atmosphere and even within the ground. These can disrupt navigation systems, radio signals, and occasionally power lines, triggering blackouts. Engineers study space weather much as meteorologists study storms, predicting flares and protecting satellites. The same energy that nourishes life can, in excess, remind us of our smallness. The sun's influence does not end at daylight. It extends into technology, orbit, and the fragile web of electricity that sustains modern civilization. The sun will shine for about 5 billion more years. The sun is middle-aged, steady, mature, and reliable. It has been burning for nearly 5 billion years and will continue roughly as long before, changing dramatically. During that time, it will gradually grow brighter as fusion in its core proceeds. The Earth's climate will slowly shift, oceans may evaporate, and life will adapt or fade. Yet from the perspective of the universe, 5 billion years is the blink of an eye. The sun's story is far from over. It remains a masterpiece in progress, the calm center of our brief human timeline. Then it will expand into a red giant. When the hydrogen in its core is depleted, fusion will shift outward into surrounding layers. The imbalance will cause the sun to swell into a red giant, hundreds of times its current size. Its surface will cool and redden, but its luminosity will soar, bathing the inner planets in fierce heat. Mercury and Venus will vanish. Earth may follow. Yet beyond destruction, the transformation will scatter new material into space, returning enriched elements to the galaxy. Even in death, the sun will give back more than it took, a final act of creation through expansion. Earth may be swallowed or scorched. As the red giant sun expands, its outer atmosphere will engulf the orbits of the inner planets. Whether Earth is consumed or merely scorched depends on complex balances of drag and loss, but in either case, its surface will become molten. The oceans will boil, the sky will burn away, and the memory of life will dissolve into vapor. Yet the atoms that once made Earth, carbon, oxygen, iron, will survive, drifting into space to seed new worlds. The end of our planet is not annihilation but transformation, the passing of matter from one home to another. The sun will shed its outer layers. After its red giant phase, the sun will release its outer layers into space, forming a glowing shell of gas known as a planetary nebula. For a few thousand years, it will shine like a cosmic flower, illuminated by the remnant core at its center. The colors, green from oxygen, red from hydrogen, blue from helium, will drift outward, merging with the interstellar medium. This ethereal beauty marks not despair, but renewal. From those gases, future stars and planets may arise, carrying forward the story that began in our own. What remains will be a white dwarf, a glowing ember. At the end, all that remains of the sun will be its core, a dense sphere about the size of Earth, composed mostly of carbon and oxygen. This white dwarf will no longer fuse atoms, but will glow from residual heat, slowly fading over trillions of years. It will be small, silent, and steadfast, a diamond of stellar memory. The last light of a long-lived star. Around it may orbit the fragments of former planets, cold and dark, witnesses to an ancient warmth that once nourished life. Even in its quietest form, the sun will still shine, faintly echoing its once brilliant heart. The light of tomorrow is already inside today's sun. Every photon that will ever leave the sun already exists in potential within its atoms, waiting to be born through fusion, to journey across space, to illuminate worlds not yet imagined. The future sunlight that will touch distant civilizations, or perhaps the final ray that will shine on Earth, is already forming in the star's core at this very moment. The sun is not merely our present source of warmth. It is the seed of every tomorrow. Its light travels not just through space, but through time, connecting the dawn of life to the farthest future of the cosmos. Massive stars live fast and die violently. Among the billions of stars scattered through the galaxies, a few are born with extraordinary mass, 10, 20, even 100 times greater than our sun. From the moment they ignite, their existence is an act of intensity. They burn through their hydrogen fuel at a frantic pace, shining millions of times brighter than smaller stars, but living only a fraction as long. In cosmic terms, their lives are over in an instant, a few million years, compared to the billions enjoyed by quieter suns. Yet during that short time they reshape their surroundings, flooding space with light, sculpting nebulae, and triggering new births. Their brilliance is inseparable from their doom. They live in excess, and when their fuel runs out, gravity claims its due in a finale so powerful it can be seen across the universe. When fusion stops, gravity wins. For a star, fusion is balance. The outward pressure of energy counters the inward pull of gravity, holding collapse at bay. But when the fuel is gone, when the core can no longer fuse hydrogen, helium, or heavier elements, that balance breaks. In a single instant, the vast energy that supported the star vanishes, and gravity, patient through millions of years, takes over. The entire core begins to fall inward, atoms crushed into oblivion. The outer layers, suddenly unsupported, follow. It is the ultimate surrender, the moment when a giant that once defied collapse succumbs to the very force that gave it shape. The core collapses in a heartbeat. Once fusion ceases, collapse happens unimaginably fast. In less than a second, a star many times the sun's mass implodes. The core contracts from the size of Earth to that of a city, densities soaring until matter itself is transformed. Protons and electrons merge into neutrons. The fabric of space bends inward. This is gravity at its most extreme, unstoppable, silent, absolute. The collapse releases a shock wave that races outward through the infalling layers. What began as implosion soon becomes explosion, as the energy rebounds and tears the star apart. A heartbeat in time, yet powerful enough to change galaxies. The outer layers explode outward, a supernova. In that instant of rebound, the star's outer shells are hurled into space at thousands of kilometers per second. A shock wave of radiation and matter bursts forth, a supernova. For weeks, its brilliance can rival an entire galaxy. The light we see from these explosions began in cataclysm, but travels peacefully through the cosmos, a reminder that even chaos can produce beauty. Supernovae are rare, yet each one marks the end of a massive star and the beginning of countless others. Their light echoes for centuries. Their debris becomes the raw material of worlds yet unborn. For a moment, it outshines a whole galaxy. Imagine a single star outshining 100 billion others. For a brief time, days or weeks, a supernova's light dominates the sky of its host galaxy. Ancient astronomers recorded them as guest stars, sudden intruders appearing where none had been before. Today, telescopes capture their afterglows across the electromagnetic spectrum, revealing expanding rings of gas and dust. That brightness, though short-lived, releases more energy than our sun will emit in its entire lifetime. The universe speaks in flashes like these, moments of overwhelming light followed by long silence, reminders that even endings can illuminate the dark. Supernovae create elements heavier than iron. Inside the collapsing core, conditions become so extreme that ordinary fusion is replaced by nuclear alchemy. Atomic nuclei are bombarded by neutrons and fused into heavier and heavier elements. Gold, silver, lead, uranium, materials that cannot form in any lesser fire. In mere seconds, the universe's inventory expands, as if creation itself takes a breath. These newborn atoms are flung outward in the explosion, mingling with interstellar gas. Every planet, mountain, and body carries traces of that ancient blast. The heavy elements that build our world were not made in peace, but in the thunder of dying stars. Gold, silver, uranium, all from dying stars. The metals that glitter in human hands were once fragments of stellar death. In the chaos of supernovae, atomic nuclei collided and captured neutrons in rapid succession, forming the heaviest elements. When the explosion faded, those atoms drifted for eons through space, gathering into clouds that would someday become new solar systems. The ring on a finger, the circuitry of a computer, the minerals in rock, each carries the memory of that violence. Wealth, technology, life itself, all trace back to the generosity of stars that burned too brightly to last. Their deaths gifted the universe its richness. Neutron stars remain, dense, spinning remnants. After the explosion, what remains of the core is compressed into a sphere only about 20 kilometers wide, a neutron star. In this tiny object, matter is so dense that a spoonful would weigh billions of tons. Its surface gravity is immense, its magnetic field beyond imagination. Many spin rapidly, completing dozens, or even hundreds of rotations each second. They are the embers of supernovae, still glowing with energy, still marking time through their rotation. Neutron stars are paradoxes. death condensed into motion, silence turned into rhythm. They are the heartbeat that continues long after the body is gone. If massive enough, they collapse further into black holes. When the original star is truly colossal, not even neutron pressure can resist gravity. The core collapses beyond all limits, shrinking into a point of infinite density, a black hole. Nothing, not even light, can escape its grip. The event horizon marks the boundary where space and time fold in on themselves. From outside, the star has vanished, yet its mass, its gravity, remains, shaping the orbits of nearby matter. Black holes are not empty. They are memory, the shadow of a star's existence preserved in gravity's absolute form. Some supernovae leave behind pulsars, rotating beacons. Among neutron stars, some emit beams of radio waves or X-rays from their magnetic poles. As they spin, these beams sweep across the sky, flashing rhythmically like cosmic lighthouses. From Earth, we detect these flashes as precisely timed pulses, hence the name pulsars. They are among the most accurate clocks in the universe, their rotation barely slowing over millions of years. Born from destruction, they serve as guides and metronomes for astronomers, marking distances and mapping gravitational waves. Even in ruin, a star finds a way to communicate, its rotation whispering across space. Steady and eternal, these stars spin hundreds of times per second. The conservation of angular momentum means that as a massive star's core collapses, its spin accelerates dramatically, just as an ice skater spins faster when drawing in their arms. A pulsar can rotate hundreds of times every second, its speed so great that the surface moves at a significant fraction of light's velocity. Yet this dizzying motion is perfectly stable, maintained for eons by the star's immense magnetic field. Each rotation emits a pulse of radiation that can be detected across galaxies. These cosmic metronomes remind us that even in decay, precision and order persist. Their radio pulses sweep across space like cosmic lighthouses. Each pulse from a neutron star travels across the void, steady as a heartbeat, precise as a clock. Astronomers use arrays of radio telescopes to capture these signals, sometimes combining them to detect subtle distortions caused by passing gravitational waves. The regularity is astonishing. Some pulsars keep better time than atomic clocks. To listen to one is to hear the rhythm of a collapsed sun, still spinning, still speaking in light and magnetism. The galaxy is filled with these lighthouses, invisible to the eye but audible to instruments, guiding our understanding of cosmic structure through their steady beacons. A teaspoon of neutron star matter weighs billions of tons. The density inside a neutron star is beyond comprehension. Matter is compressed until atoms lose their individuality, electrons and protons combine into neutrons, packed shoulder to shoulder. 1 cubic centimeter, smaller than a sugar cube, weighs as much as a mountain. Space-time itself bends under that weight. These remnants push the limits of physics, where quantum mechanics and gravity meet. To hold even a fragment of such matter would be impossible. It would sink through the earth to its core. Yet within that unimaginable compression lies one of the universe's purest forms of structure, matter as tightly woven as reality allows. Gravity there is so strong light bends around it. Near a neutron star, gravity warps space to such a degree that light no longer travels in straight lines. Photons curve around the surface, allowing observers to see parts of the star that should be hidden. In even stronger gravity, such as near a black hole, light may orbit entirely, trapped in loops of distortion. To witness these effects is to see Einstein's equations alive, space itself behaving like a fluid shaped by mass. Gravity does not simply pull, it sculpts perception. In these dense remnants, the universe reveals its flexibility, bending light into poetry. Even death in the cosmos becomes creation. A star's death is not an ending, but a transition. The explosion spreads enriched matter through space, while the remaining core becomes a neutron star or black hole. From destruction come the ingredients for life: carbon, oxygen, iron, calcium. The debris of one generation becomes the nursery of the next. In this sense, stars are reincarnated endlessly, their matter and energy recycled. Across time, the cosmos knows no true death, it only transforms. Every loss in the heavens is matched by renewal elsewhere, an unbroken loop of creation through change. The shockwaves seed new nebulae. As supernova shockwaves sweep through interstellar space, they compress nearby clouds of gas and dust, triggering new rounds of star formation. What began as the death cry of one star becomes the cradle of others. These expanding shells, glowing in ultraviolet and X-rays, mix elements into the galactic medium. Nebulae such as the Veil and the Cygnus Loop are examples: vast, delicate veils of light that drift for thousands of years, spreading the materials of future suns. The universe plants its seeds with explosions, cultivating new brightness from the ashes of the old. Out of destruction, new stars arise. Over millions of years, the gas and dust enriched by a supernova cool and gather once more under gravity. Dense knots form, collapse, and ignite, giving birth to a new generation of stars. Some may host planets, perhaps life, perhaps observers who will one day study the light of their ancestors. The cycle continues: birth, brilliance, death, rebirth, an unending chain linking every atom of existence. When we gaze at the sky, we are seeing the aftermath of countless such cycles. The stars above are not ancient strangers, but our own lineage, reborn in infinite forms. Supernova remnants form rings and filaments of light. Long after the explosion fades, the debris continues to expand, forming intricate structures of gas and dust. Under telescopes, these remnants appear as luminous filaments, twisted arcs, and glowing rings, cosmic embroidery against darkness. Each color represents a different element: red from hydrogen, green from oxygen, blue from sulfur. Over thousands of years, these shapes stretch and fade, merging into the interstellar medium. They are the visible memory of death, light sculpted by shock and time, beauty born from energy's last breath. The Crab Nebula is one such echo of death. In 1054 AD, observers in China and the Middle East recorded a brilliant guest star that shone even in daylight for weeks. It was a supernova in the constellation Taurus. Today, its remnants form the Crab Nebula, a vast, tangled cloud still expanding, still glowing. At its center spins a pulsar, the collapsed heart of the original star, flashing 30 times a second. The light we see now is a continuation of that thousand-year-old explosion. The crab reminds us how fleeting human history is, beside the rhythms of the cosmos, and how long light can carry memory across the dark. Every night sky glows with the ashes of ancient stars. The light that reaches us from the Milky Way is not merely from living stars. It is also reflection, photons scattered by interstellar dust, energized by the debris of long-dead suns. The glow of the galaxy is a tapestry woven from past lives. Each twinkle, each faint shimmer, contains atoms forged in forgotten explosions. When you look up at night, you are seeing not only what is, but everything that was, the silent residue of creation, continuing to shine. The universe never truly lets go of its dead. It turns them into light once more. Red giants are dying stars in their final expansion. When a sun-like star nears the end of its fuel supply, its balance begins to slip. Hydrogen fusion in the core fades, shifting outward to a surrounding shell. The star responds by swelling, layer upon layer inflating like a great luminous balloon. Its outer atmosphere cools and reddens, glowing softly instead of burning hot. What was once a stable yellow sun becomes a vast red sphere hundreds of times larger than before. In that transformation lies both decline and grandeur, a life reaching its final fullness. Through the thin gas of a red giant's surface, you could drift in silence, seeing the stars' light diffused. Like sunrise through mist, a gentle farewell written in fire. They grow large as their cores fuse helium. Inside the swollen body of a red giant, fusion continues, but now it burns helium into carbon and oxygen. The process is more intense, producing surges of energy that cause the star's outer layers to pulse and shimmer. The core, meanwhile, contracts and heats, becoming a dense, white-hot ember at the center of that vast envelope. The star's light wavers between brilliance and calm, a rhythmic breathing that may last millions of years. In this phase, matter rearranges itself. Once again, elements that will someday form worlds, oceans, and bones are forged quietly beneath those red veils. Some swell to engulf their planets. As the star expands, its reach extends far beyond its original orbit. Planets that once circled safely may find themselves drawn into the growing inferno. Mercury, Venus, even Earth, could one day be swallowed when our own sun becomes a red giant. The pull of the swollen atmosphere drags planets inward, stripping them of surface and sky until they vanish. Yet this destruction is not meaningless. The material they add feeds the star's glow for a final time. In the cosmos, even loss becomes fuel for light. White dwarfs are their quiet afterlife. When the outer layers drift away, the core remains, a small, dense sphere glowing with residual heat. This is a white dwarf, the final, peaceful stage of most stars. About the size of Earth, but holding half the sun's mass, it no longer fuses atoms. It merely cools, shining softly for billions of years. Its gravity is immense, its surface pure brilliance. No storms rage there, no flares erupt. Only a slow fading into silence. A white dwarf is a cosmic memory, the soul of a star that has given everything it had to give. Brown dwarfs hover between planets and stars. Not all collapsing clouds succeed in igniting fusion. Some gather just enough mass to glow dimly from heat, but never reach the threshold for sustained burning. These are brown dwarfs, cosmic in-betweens, halfway between giant planets and true stars. Invisible to human eyes, they radiate an infrared light. Warm but dark, they drift quietly through space, solitary or accompanied by planets of their own. In their subdued glow, the universe reveals its gray zones, the gentle gradient between success and stillness. Even in almost stars, there is dignity, a reminder that not all fires need to blaze to matter. Blue supergiants burn with furious intensity. At the opposite extreme stand the blue supergiants, titans of heat and energy. Their surfaces blaze above 30,000 degrees, and their luminosity rivals millions of suns. They live only a few million years before dying in spectacular explosions, but during that brief existence they dominate their regions of space, ionizing nearby gas and shaping entire nebulae. To gaze upon one is to witness the universe in overdrive, beauty, and violence combined. Their light travels far, piercing cosmic dust to remind us that even brief brilliance can define an age. Some stars, like Betelgeuse, may soon explode. In the constellation Orion, Betelgeuse glows with a deep orange hue, its surface already trembling with instability. It is nearing the end of its life as a red supergiant, its core preparing for collapse. One day, tomorrow or 100,000 years from now, it will erupt as a supernova, outshining the moon in our sky. For a few weeks, night will turn to day, and humanity will witness the death of a neighbor star. Yet the atoms that burst forth will seed new generations of suns. Betelgeuse's final breath will be both spectacle and gift. Hypergiants are among the rarest stars known, even more massive than blue. Supergiants. Hypergiants exist at the limits of what physics allows. They can be hundreds of times the sun's mass and 1,000,000 times as luminous. Their lives are measured in mere millions of years. But their output shapes galaxies. Stellar winds from hypergiants blow off entire layers of matter, creating nebulae visible across vast distances. They are the universe's extravagance, rare, unstable, magnificent. In their enormous size and fleeting presence, they remind us that scale is not permanence. Even giants must fade. Wolf-Rayet stars lose mass through powerful winds. A Wolf-Rayet star is a supergiant stripped bare. Its fierce winds, traveling at thousands of kilometers per second, blow away its outer layers, exposing the blazing core beneath. These winds enrich surrounding space with carbon, nitrogen, and oxygen, the raw materials for life. The star itself shines with a pale, spectral blue, its surface temperature exceeding 50,000 degrees. Wolf-Rayet stars are both dying and giving, shedding themselves into the galaxy like dandelions scattering seeds. Their violence is generosity in disguise. Magnetars are neutron stars with extreme magnetic fields. Among the strangest remnants of stellar death are magnetars, neutron stars whose magnetic fields are 1,000 trillion times stronger than Earth's. In these exotic objects, magnetic energy twists the crust until it cracks, releasing bursts of X-rays and gamma rays. Their power defies comprehension. A single flare can outshine the sun's total yearly output. Yet they are tiny, only about 20 kilometers across. To encounter a magnetar is to glimpse nature's extremes compressed into something no larger than a city, a monument to the strength hidden in collapse. Their magnetic strength could erase data from a planet away. If a magnetar passed within a few 100,000 kilometers of Earth, its magnetic field would wreak havoc on every atom of metal, scrambling electronics, and possibly tearing molecules apart. Thankfully, none lie close enough for such danger. But the idea illustrates their enormity, invisible forces reaching across unimaginable distances. Magnetars turn gravity into magnetism, silence into potential catastrophe, yet they also teach us humility. Their existence proves that nature's imagination exceeds our own, sculpting possibilities that defy comfort yet inspire awe. Some stars emit X-rays or gamma rays. Not all starlight is visible. Some stars, especially compact ones like neutron stars and white dwarfs, in binary systems, release their energy as high-frequency radiation. X-rays and gamma rays reveal the most energetic processes in the universe: accretion disks, jets, and collisions. Through space telescopes tuned to these wavelengths, astronomers watch invisible fireworks play out, matter spiraling inward, heating to millions of degrees before disappearing into silence. These forms of light remind us that the cosmos is more than what eyes can see. It is a spectrum of unseen stories, unfolding in frequencies of power and mystery. Binary systems can steal each other's matter. In pairs of closely orbiting stars, gravity can pull material from one to the other, forming streams of gas that spiral between them. The more massive or compact partner, often a white dwarf or neutron star, becomes a thief, drawing its companion's outer layers into an orbiting ring. This cosmic exchange changes both stars. One grows brighter, the other weaker. It's a dance of attraction and loss, played out over millennia. Through this theft, new bursts of fusion ignite, lighting space with sudden flares, passion and consequence entwined in stellar form. These feeding stars form accretion disks. The stolen gas doesn't fall straight onto its companion. It swirls into a disk, heating as it spirals inward. Friction and compression raise the temperature until it glows intensely in ultraviolet and X-rays. Such disks can outshine the stars themselves. In the case of black holes, the disk marks the last visible trace of matter before it vanishes beyond the event horizon. Accretion is nature's spiral, destruction turned luminous, gravity and motion weaving together until light itself is spun from falling dust. Some explode as type I supernovae. When a white dwarf in a binary system gathers too much stolen mass, it crosses a threshold of instability. Carbon ignites throughout its interior, triggering a runaway fusion reaction. The star detonates in a thermonuclear explosion, a type I supernova. For a few weeks it can outshine its entire galaxy. Unlike the collapses of massive stars, this death leaves no remnant behind. The white dwarf is completely undone, yet its brightness follows a consistent pattern, allowing astronomers to use these explosions as cosmic yardsticks, measuring distance by the uniform brilliance of destruction. Such explosions help measure cosmic distances. Because type I supernovae reach nearly the same peak luminosity, they serve as standard candles. By comparing their observed brightness to their known true brightness, scientists can calculate how far away they are. Using these cosmic lighthouses, we discovered that distant galaxies are receding faster than expected, evidence that the universe's expansion is accelerating. Thus, the death of a single star helped reveal dark energy, one of the universe's greatest mysteries. Even endings can enlighten. Even annihilation can measure the infinite. Some systems flicker unpredictably, chaotic but beautiful. In binary pairs, accretion disks and magnetic fields can interact in unpredictable ways. Brightness surges, fades, and returns without warning. To observers, these flickers are mesmerizing, chaotic signals of balance continually found and lost. Behind the apparent randomness lies exquisite physics, gravity, rotation, heat, and magnetism locked in eternal tension. The light that flickers across our telescopes is the visible signature of turbulence, a reminder that even disorder can create patterns of grace. Even dying stars have a rhythm. Whether through pulsation, rotation, or periodic eruption, many fading stars continue to mark time. Their light rises and falls. Their shells expand and contract. Their remnants spin in steady cadence. It's as though the universe refuses abrupt silence. Every ending fades in rhythm, like a song's final notes stretched across space. These rhythms, measured in seconds or millennia, are the heartbeat of cosmic continuity, transitions expressed in light rather than sound, in timing rather than words. Every variety of star adds texture to the universe. The cosmos is not uniform. It is textured by diversity. From red dwarfs to blue giants, from pulsars to black holes, each kind of star contributes something unique. Heat, elements, radiation, structure. Together they paint the Milky Way's luminous fabric, a mixture of hues and intensities. Without variety, galaxies would be monotone. With it, they shimmer with endless nuance. The sky's beauty lies not in sameness, but in difference, a celestial harmony composed of countless distinct voices. They are the vocabulary of creation. Stars are the words with which the universe speaks matter into being. Each type, each color, each stage of life is a syllable in that grand cosmic language. Together they tell the story of transformation, gas to fire, fire to dust, dust to life. To learn their classifications and behaviors is to learn the alphabet of existence itself. Through stars, the cosmos communicates its thoughts in light, writing across the darkness for those patient enough to read. And as long as one star burns, that language, the vocabulary of creation, will never fall silent. Galaxies are cities of stars. If the universe were a vast dark continent, then galaxies would be its glowing cities, immense congregations of light and matter, each with its own structure and rhythm. Within their bounds, billions or even trillions of stars coexist, orbiting a shared center, bound together by gravity's invisible architecture. Clouds of dust form the streets where stars are born. Clusters become neighborhoods, glowing arms. The illuminated avenues spiraling outward. Seen from afar, a galaxy resembles a living organism, luminous, rotating, breathing in slow motion. Every star, every planet, every beam of light we know belongs to one of these cities, small and immense all at once. The Milky Way alone contains over 200 billion. Our home galaxy, the Milky Way, stretches 100,000 light-years across and holds at least 200 billion stars, perhaps twice that number if we count the faint and hidden. To look up on a clear, moonless night is to see only a tiny fraction of this cosmic metropolis. The soft river of light that arcs across the sky is the Milky Way seen from within. Countless suns whose combined glow forms a band of ghostly radiance. We are residents of one ordinary suburb in this vast city, orbiting quietly among its hundreds of billions of neighbors, sharing its slow galactic spin. Most galaxies have a black hole at their center. Deep in the heart of nearly every large galaxy lies a supermassive black hole, millions or billions of times the mass of our Sun. Though invisible, its gravity shapes everything around it. Stars orbit this central darkness the way planets orbit the Sun, tracing elegant paths in a dance that spans ages. When matter drifts too close, the black hole feeds, releasing jets of energy that can outshine the galaxy itself. These monstrous cores are both destroyers and regulators, maintaining galactic balance through their appetite, ensuring that creation and consumption remain in harmony. Stars orbit this gravitational heart. The Sun, and all the stars you see, are bound to this unseen center, the black hole called Sagittarius A star. It lies about 26,000 light-years away, hidden behind thick clouds of dust, revealed only through radio and infrared eyes. Our solar system, along with billions of others, moves in a grand circular journey around it. Each orbit takes roughly 230 million years. The last time the Sun was in this position, the first dinosaurs were just beginning to roam the Earth. Every night sky you see is a single snapshot of this slow, majestic rotation, an ocean of stars flowing around an invisible anchor. Spiral galaxies have winding arms filled with young stars. Spiral galaxies, like our Milky Way, are among the most beautiful structures in the cosmos. Their arms curl outward from a bright central bulge, tracing graceful patterns of light and dust. These arms are not solid structures, but waves of density, regions where gas clouds compress and ignite, birthing new stars. Within them, blue-white clusters sparkle with youth, while older, redder stars drift toward the center. The spiral form is nature's signature of motion and renewal, a cosmic fingerprint repeated across billions of galaxies, each one a slowly turning wheel of creation. Elliptical galaxies are older and redder, while spirals are youthful and dynamic. Elliptical galaxies are mature, smooth, round, and filled mostly with aging stars. They have little gas left to form new suns, so their light glows a gentle amber. These galaxies are often the result of collisions, their once distinct shapes blended into a vast, diffuse whole. In their quiet, they represent cosmic retirement, not lifeless, but settled, content to shine softly without the turbulence of new birth. They are the elders of the universe, holding within them the long memory of light. Irregular galaxies are shaped by collisions. Not all galaxies are orderly spirals or smooth ellipses. Some are distorted, stretched, or twisted, irregular forms sculpted by gravitational encounters. When galaxies pass close to one another, their mutual pull can tear them apart, flinging stars into bridges and tails of light. These interactions are not rare. They are part of galactic evolution. Over time, chaos settles into new order, just as a storm eventually becomes calm. The strange shapes we see in irregular galaxies are snapshots of that transformation, fleeting gestures in an endless cosmic dance. New stars form where gas clouds collide. In the meeting places of galaxies, where vast clouds of gas crash. Together, shockwaves compress matter until it collapses under its own gravity. In those regions, the dark void ignites. Entire clusters of stars can be born in a single burst of creation, their light spilling across space. These stellar nurseries are the cosmic equivalent of rainforests, dense, fertile, full of energy and renewal. Even destruction feeds them when galaxies merge. Their collisions become engines of new light. The universe wastes nothing. Every impact becomes an opportunity for rebirth. Starburst galaxies produce thousands of stars per year. Some galaxies enter frenzied periods of formation, creating thousands of new stars each year, far more than the few our Milky Way manages. These starburst galaxies shine intensely, their cores crowded with luminous clusters. Yet this pace cannot last. In only a few 100 million years, their gas supply is exhausted, and the burst fades into calm. Like fireworks, their brilliance is brief but unforgettable. Flashes of creativity that reshape the universe in concentrated waves of light. They remind us that even galaxies have moods, quiet centuries punctuated by sudden, radiant creation. In contrast, others are quiet and fading. Not every galaxy burns with activity. Some have already spent their reserves of gas, leaving only old stars and fading light. These galaxies drift through time like cooling embers, dim but dignified. Their silence is not failure, it is rest. They have lived their active lives, forged their elements, and now contribute their mass to the slow architecture of the cosmos. Even in their twilight, they continue to hold structure, guiding smaller galaxies, shaping gravitational tides. In stillness, they persist, reminders that not all beauty depends on brightness. Our sun orbits the Milky Way once every 230 million years. The solar system moves through the galaxy at about 828,000 kilometers per hour, tracing a vast, invisible curve around the center. One complete orbit, a galactic year, takes 230 million Earth years. Since the sun's birth, it has made roughly 20 such revolutions. During that time, continents have formed and vanished, species have risen and fallen, civilizations have appeared in a blink. To the galaxy, our entire human story is less than a moment in a single turn of its spiral. We are travelers aboard a moving star, circling the Milky Way's luminous heart. It has done so about 20 times since birth. Imagine the timeline of the solar system stretched like a clock, 4.6 billion years marked by 20 full galactic orbits. In its first, the Earth cooled and the first oceans formed. By the fifth, life had taken hold. By the 17th, dinosaurs walked beneath a younger sun. We live now in the 20th. Our age, a brief flicker near the edge of that cosmic loop. The galaxy spins slowly, but life within it moves quickly, like sparks dancing around a bonfire that burns. For eternity, the night sky we see is one moment in that journey. Every star we see tonight is part of that grand rotation, each with its own orbit, speed, and trajectory. Yet from our small point of view, the sky seems still. What we perceive as fixed constellations are actually rivers of motion frozen by scale. Over millions of years, the shapes of Orion, Lyra, and Cassiopeia will drift apart, rearranging into new patterns. The night sky is a photograph in motion, a single frame from an ongoing galactic voyage. When we look upward, we're watching a procession too vast to notice it moving. The Milky Way itself will someday merge with Andromeda. Far across the sky, another spiral galaxy, Andromeda, approaches us at 400,000 kilometers per hour. In about 4 billion years, it will collide with the Milky Way. Yet this collision will not be violent in the way we imagine. The space between stars is immense. They will mostly pass through one another unharmed. Gravity will weave their structures together, forming bridges of light, tidal tails, and new clusters. For a time, the night sky from any surviving world will blaze with thousands of suns. From two spirals, a new, larger galaxy will be born. Their stars will dance, but rarely collide. Despite the word collision, galaxies merge gracefully. Their stars move like grains of sand carried in overlapping currents, weaving through each other without touching. What collides instead are their clouds of gas, compressing to spark new generations of stars. The process unfolds over billions of years, slow, majestic, soundless. When the dance is done, the result is a new shape, often an elliptical galaxy glowing with the combined light of both parents. Even in cosmic union, the universe remains patient, allowing grandeur to unfold at the pace of gravity. Gravity will sculpt a new elliptical galaxy. After the merger of the Milky Way and Andromeda, the spiral's delicate arms will dissolve, replaced by a smooth, rounded form. Astronomers already have a name for the future product, Milkomeda. Within it, the merged black holes of both galaxies will settle at the center, surrounded by billions of stars in new orbits. The view from any surviving planet will be breathtaking. An entire sky filled with light, no dark space left between galaxies. The new shape will mark not an ending, but the next chapter of galactic evolution, form yielding to symmetry, motion to stillness. Even galaxies grow old. Galaxies, like stars, have life cycles. They are born from clouds of gas, grow through mergers and star formation, and eventually fade as their material is used up. The universe today is less fertile than it once was. New galaxies form. Rarely now. Over trillions of years, many will dim completely, their stars burned out, their light gone. Yet their structures will remain, silent fossils adrift in the expanding dark. Galaxies remind us that nothing, not even vastness, escapes time. Immortality in the universe is not stillness, but renewal. Yet stars continue to form in their dusty hearts. Even in aging galaxies, dense pockets of gas and dust persist, sheltered regions where gravity can still ignite new suns. In these nurseries, the next generation of light gathers quietly, repeating the ancient pattern of birth and burn. The galaxies themselves may slow, but their hearts never stop completely. As long as matter exists, there will be stars. As long as stars exist, there will be light. The rhythm continues, faint but eternal, like the embers of a fire that refuses to die. The cosmic web links all galaxies together. Zoom out far enough. Vast network of filaments and clusters stretching across the universe. This cosmic web is woven from dark matter and gas, its threads connecting galaxies like beads on invisible strings. Where the filaments, another. Every star is a point in that grand design, a node in the network of illumination stretching from here to the edges of time. Together, galaxies and their stars form a cosmic web of radiance. An interconnected system where gravity is the wiring and light the signal. Each photon that leaves a star joins this web, traveling endlessly, linking one region of space to another. The universe is not isolated parts, but one luminous fabric. Stars, galaxies, and observers all entangled in the same glowing whole. Through them, the cosmos writes its name in light. Every star is both ancient and new. When we look up at the sky, every point of light is a paradox. Each star has existed for millions or billions of years, yet the light reaching our eyes is new, freshly arrived, completing a journey across the vast ocean of space. In that moment of arrival, something ancient becomes present. Every star is in the act of becoming, aging, evolving, transforming, even as its glow feels timeless. Within it both the memory of creation and the promise of continuation, proof that in the cosmos, age and youth are not opposites, but companions. The light we see tonight began before we were born. Every photon entering your eye this evening began its journey long before you existed. The light from nearby stars may have been traveling for decades, from distant ones, for centuries. Some began when humans first painted on cave walls. Others left their stars before any life on Earth had yet spoken. What you see tonight is not happening now. It is history carried by light. In that sense, the night sky is an archive of the universe's memory, a living time machine surrounding our planet. When you gaze upward, you are not just looking at distance, you are looking at time itself, shimmering quietly across the dark. Some of it began before Earth existed. Far beyond the nearby stars, galaxies shimmer whose light has been traveling for billions of years. Some of those photons began their journey before our planet formed, before the sun ignited, before even the elements of life existed. By the time that ancient light reaches us, entire civilizations of stars have lived and died. The earth, the oceans, the people who now watch that light, all appeared while those photons were still on their way. Each beam that touches your eye is older than our world, yet it finds you now, precisely in this moment, as though time and distance were just illusions through which the universe whispers, "I've been waiting for you to look." Stars remind us that time is vast and patient. Human lives measure time in years, centuries at most. Stars measure it in billions. Their slow rhythms, the birth, growth, and fading of light, unfold so gradually that even civilizations come and go in what, to them, is the blink of an eye. Watching them teaches humility, that patience is not absence, and slowness is not stillness. The stars do not hurry to shine, nor do they rush to die. They remind us that endurance is beauty, that the universe's greatest works are written not in moments, but in epochs. They burn their lives for others to see. Every glimmer in the night sky is a sacrifice. A star consumes itself to give light. It spends its existence transforming matter into energy, radiating warmth and illumination into the darkness. In that quiet act, it becomes both creator and giver. The light it shares nurtures planets, awakens life, and carries meaning across the void. A star never sees the worlds it warms, never witnesses the eyes that will admire it. It shines regardless, selflessly, inevitably. To burn is its purpose, and in doing so, it becomes a mirror for the deepest truth of creation. That light is born from giving. The atoms in your eyes once burned inside a star. The carbon that shapes your cells, the oxygen that fills your lungs, the calcium in your bones, all were forged long ago in the hearts of stars. When those stars died, they scattered their elements across space, and over eons, those atoms gathered again into clouds, planets, oceans, and life. You are the universe, made aware of itself, a constellation rearranged into consciousness. The light you see and the eyes that see it are built from the same matter, recycled through generations of suns. Every heartbeat is fusion remembered, every thought, a ripple of starlight returning home. To look at starlight is to look into yourself. When you gaze upward at the stars, you are not merely observing something distant, you are recognizing kin. The light that reaches your eyes resonates with the same origins as you. The atoms that make you were once part of stars, the photons that touch. You were born from their burning. You are both the observer and the observed, a reflection of the same cosmic process. To look at starlight, then, is to participate in a reunion, a brief moment of recognition between fragments of the same whole. You are not separate from the sky. You are its continuation. The cosmos does not waste, it transforms. In the universe, nothing is lost. Matter becomes energy, energy becomes matter, stars become dust, dust becomes new stars. Every death is a rearrangement, every collapse a new beginning. The cosmos recycles itself endlessly, using the remnants of old creations to form new possibilities. The same particles that once drifted in ancient nebulae now form your heartbeat, your breath, your dreams. Nothing disappears. Everything changes shape. The universe is not a story of endings, but of transformations, an eternal dance of becoming. Stars are engines of creation, but also of memory. Within each star's core, fusion does more than generate light, it records the past. Every layer of a star tells the story of what it has burned and when, preserving the sequence of elements it has made. When the star dies, those elements are written into the galaxy, scattered across space, absorbed by clouds, woven into the chemistry of new worlds. In that way, every atom carries history, the memory of heat, pressure, and light that once existed at a star's heart. To study starlight is to read the memory of matter itself. They record the story of matter in their cores. A star's interior is like a time capsule of the universe. The simplest atoms, created in the Big Bang, enter its gravity, and through fusion they are transformed, step by step, into the elements of life. Those layers remain until the stars end, when an explosion or slow shedding of gas releases them. In their cores, stars chronicle the evolution of complexity, showing how the cosmos learned to build from simplicity. Their light is not random. It is a signature, a coded record of all that came before. In their depths, the history of existence burns quietly, line by line. When they die, they write it into space. The death of a star is the act of release, the moment when everything it has created within is shared with the universe beyond. The carbon, oxygen, iron, and gold that it formed are cast outward, filling space with possibility. Each explosion, each slow fading wind, becomes a page added to the great cosmic story. The universe grows richer with every stellar death, more diverse, more alive. In this way, stars are not only the authors of matter but also its publishers, their endings written across the galaxies in trails of light and dust. Life is how the universe remembers. Stars burn, planets form, and in rare places, chemistry begins to think. Life is the universe's way of keeping record, of experiencing itself. Through living beings, matter becomes aware of its own origins. The atoms forged in stars now contemplate those same stars, reflecting their light and thought. In us, the cosmos achieves self-observation, memory given voice. Every idea, every feeling, every moment of wonder is the universe remembering itself through consciousness, fleeting yet profound. We are not separate from creation. We are its continuation into awareness. Even silence between stars holds potential. Between the galaxies lies vast darkness, cold, thin, and seemingly empty. Yet even there, faint atoms drift, seeds waiting for gravity's pull. The silence is not absence but rest, a pause in the cosmic rhythm. Given time, those particles will gather, collapse, ignite, and new stars will be born. The quiet between lights is the inhale between breaths, the waiting before the next act of creation. The universe is never still. It simply moves in cycles of sound and stillness, explosion and calm. The night sky is not empty. It is waiting. What looks like darkness is not void, but depth. Behind the visible stars lie countless others too distant or faint to see. Between them, nebulae, galaxies, and worlds drift unseen. Every patch of darkness hides a multitude of light waiting to emerge. Even the empty sky is rich with invisible energy, with potential for stars yet unborn. The universe is not a stage where things appear and vanish. It is a constant unfolding, an infinite pause before infinite becoming. When you look at the dark, know that it is not empty. It is expectation made visible. Stars teach patience and impermanence. No star rushes. No star lasts forever. Each one burns at its own pace, a balance between endurance and release. Some blaze quickly and die young. Others smolder quietly for trillions of years. Their lives remind us that existence is not measured by duration, but by transformation. A star does not fear its end. It becomes its end, seamlessly, naturally. In that example lies a quiet lesson that change is not loss, but the rhythm by which the universe breathes. They remind us that endings are beginnings in disguise. Every dying star becomes the cradle of new stars, planets, and life. What seems like destruction is merely reorganization, matter reshaped into new forms of light. Supernovae give rise to nebulae. Nebulae birth new suns. The universe never stops recycling itself, and in doing so, it never truly ends. To see a star's death is to witness continuity, not catastrophe. Endings in the cosmos are doorways, the closing of one brilliance so another may ignite. To study a star is to study transformation. Astronomy is more than observation, it is meditation. In studying stars, we study how everything changes. Matter into light, light into time, time into memory. A telescope is a mirror pointed outward but also inward, revealing how we, too, are shaped by the same forces. The fusion that powers the sun also powers our cells. The cycles of burning and cooling mirror our own cycles of creation and rest. The science of stars is not distant knowledge. It is a philosophy of impermanence made visible. To sleep beneath them is to share in that rhythm. When we lie beneath the stars and let the mind drift, we synchronize, breathing with the slow pulse of the cosmos. The stillness of the night is not isolation but communion. The light above has traveled across millennia to reach this exact moment, touching your closed eyelids as you rest. In that soft connection, the universe cradles you in its continuity. Sleep itself becomes a mirror of cosmic rhythm, expansion and collapse, energy and silence, awareness and surrender. Beneath the stars, rest is not escape, it is participation. Every flicker of light is a whisper from creation. The faintest shimmer in the night is a message carried across time and space. Each photon tells of fusion, of gravity, of survival against collapse. When you see it, you are receiving the memory of creation itself, not metaphorically, but literally. That light began as an act of birth, endured endless travel, and found its way to your eyes. The universe speaks gently in photons and silence, saying only, I am still here. I am still becoming. The stars are not distant. They are within everything. It is easy to think of the stars as far away, but in truth, they are everywhere, in the atoms that form our bodies, in the light that shapes our days, in the energy that fuels our thoughts. We are not observers looking up from below. We are participants in the same cosmic process. The stars are the universe looking at itself through us, burning within and without. When we gaze upward, we are seeing not separation, but reflection, the recognition that everything shining above is already part of what we are. The universe is slowly running out of new stars. When the cosmos was young, star birth was everywhere. Galaxies blazed with newborn light. Gas clouds collided in dense, glowing chaos. But over billions of years, that abundance has waned. The raw material for creation, hydrogen and helium gas, has been used up or dispersed too thinly across space to collapse. Again, today, the rate of star formation is a fraction of what it once was. Each generation of stars leaves behind fewer clouds to take their place. The night sky still burns with beauty, but it is the echo of an age when creation was faster, louder, and more alive. Gas clouds are thinning, creation slows. The galaxies that once thrived with star-forming regions now grow quieter. Their clouds of gas stretch and scatter, diluted by supernova winds and cosmic expansion. As the gas thins, gravity struggles to pull it together. In distant epochs, new stars will still emerge, but, rarely, faintly, in isolation. The universe is entering a gentler chapter, a time of fading fire and cooling light. Creation has not stopped, it has slowed to a whisper. The grand furnaces still burn, but their fuel runs low, and their song is becoming a lullaby. Red dwarfs will outlast all others. The last generation of stars will not be giants or suns like ours. They will be red dwarfs. Small and steady, burning their hydrogen with exquisite efficiency, they will live for trillions of years, glowing softly like embers in the dark, long after every blue and white star has died. Red dwarfs will continue to warm their tiny planets, casting faint red glows into the thinning night. They are the universe's slow heartbeat, its patient survivors. When all else has faded, they will remain, quiet, enduring witnesses to time's final chapters. When they die, darkness will spread. Even red dwarfs cannot last forever. One by one, they will exhaust their fuel and fade, leaving behind cooling white dwarfs, dim relics of what once was. As each light goes out, the universe will grow darker. The galaxies that now shine like jeweled spirals will dim to faint outlines, then vanish entirely to human eyes. Night will become universal, a silence without sunrise. Yet that darkness will not be emptiness. It will be rest, the cooling breath after a long and luminous creation. White dwarfs will cool into black dwarfs. The remnants of stars, white dwarfs, will continue to radiate their stored heat for trillions upon trillions of years, gradually fading into cold, invisible objects known as black dwarfs. These will no longer shine or warm. They will simply exist, carbon and oxygen frozen into quiet spheres. The universe will become a vast graveyard of these stellar fossils, each one holding the memory of a sun that once was. The stars will not be gone, only asleep, their fire banked forever. The light of creation will linger as warmth in the void, slowly vanishing into stillness. Galaxies will fade to red embers. As the youngest, hottest stars die first, the overall light of galaxies will redden. Over eons, they will glow faintly in infrared, their once luminous arms now ghostly and diffuse. The bright blues of youth will be gone, replaced by the long, slow radiance of aging suns. Eventually, even that light will fade, and galaxies will become invisible to any remaining eyes. The universe will resemble a field of cooling coals after a great fire, the last warmth of a cosmic evening. Even fusion will someday cease. Fusion, the process that has powered every star, depends on matter being close enough and hot enough to collide. But as the universe expands and cools, those conditions will disappear. In the far, far future, not even the densest remnants will have the energy to ignite new fires. The last fusion reactions will flicker out like the final sparks of a dying flame. The cosmos will enter an era without new light, a time of fading heat and increasing quiet, where energy becomes too thin to gather. Creation will give way to endurance, yet gravity will still shape silent ruins. Even when fusion is gone, gravity will continue its slow work. black dwarfs, neutron stars, and black holes will drift and merge, forming new constellations of darkness. Collisions may send out gravitational waves, ripples in space-time, faint murmurs of movement in the quiet. Though the universe will no longer shine, it will still move, still change, still follow its laws. Creation will continue in form, if not in light. The cosmos, even at rest, will remain elegant, a sculpture shaped by invisible forces, held together by the memory of energy that once was. Black holes will evaporate in Hawking radiation. Even black holes, the ultimate prisons of gravity, are not eternal. Over unimaginable timescales, they will slowly lose mass through quantum effects. A faint emission called Hawking radiation. For trillions upon trillions of years, they will shrink, grow weaker, and eventually vanish in a final burst of energy. The universe will see its last. Fireworks, then, the final size of gravity releasing what it held. When the last black hole fades, the cosmos will be left almost empty, save for stray particles and whispers of background energy. The fire that began in the Big Bang will have found its quiet end. The last light may come from a dying proton. Even the building blocks of matter, protons, may not last forever. Some theories predict that after unimaginable spans of time, they will decay, releasing faint flashes of energy. Those tiny bursts will be the last visible light in the universe, brief as fireflies in an endless night. After that, the cosmos will become truly dark, not because it has died, but because it has finally finished its long transformation. The last glimmers of matter will dissolve into energy, completing the circle that began at creation's dawn. But even then, the memory of stars remains. When the universe finally cools into silence, it will still carry the record of everything that came before. The distribution of atoms, the faint glow of background radiation, the gravitational fingerprints of vanished galaxies, all will preserve the memory of the stars. Like fossils of light, these traces will remain, whispering the history of fire that once filled space. The universe, even in darkness, will remember itself. Memory is not a thing that needs light. It is written in the shape of existence itself. Every atom they made continues its journey. The stars may fade, but their work endures. The atoms forged in their hearts will drift forever, scattered by winds, carried by gravity, woven into whatever remains. They will continue to move, collide, and combine in patterns beyond imagination. In that endless motion, the essence of starlight persists. Matter never stops. It simply finds new ways to exist. Even when the sky is dark, those atoms will still tell the story of their origin, fragments of brilliance traveling through eternity. New forms may rise from that cosmic dust. Perhaps, in ways we cannot yet imagine, the universe will recycle itself once more. Out of the remnants of the old, the cooled ashes of stars, and the faint hum of radiation, something new might emerge. A fluctuation, a gathering, a spark of creation beyond our current physics. The cosmos has reinvented itself before. It may do so again. From the Big Bang's fire to the quiet of the deep future, its pattern has always been one of transformation. Perhaps even in final silence, the seeds of another beginning will wait, sleeping beneath the dust of eternity. Perhaps stars will reignite in some distant rebirth. Some theories suggest that the universe's expansion may one day reverse, that gravity could pull everything back into a great collapse, a big crunch. If so, the cosmos might be reborn, its matter recompressed into new fires, new stars, new time. Or perhaps quantum fluctuations will create new universes altogether, each with its own beginning. The details are uncertain, but the idea is eternal, that light never truly ends, it only changes its form. Every end carries the seed of its own renewal. Or perhaps the universe will rest, quiet and complete. If expansion continues forever, then eventually, galaxies will drift apart until their light can no longer reach one another. Time will stretch, energy will cool, and motion will slow toward stillness. This is not tragedy, it is peace. The universe, having spent its vast energy in the making of stars, planets, and life, will finally rest. Every atom will have played its part. Silence will not be absence, but completion, the deep exhale after eons of creation's song. Either way, the stars will have done their work. Whether the universe burns anew or fades into stillness, the stars will have fulfilled their purpose. They transformed simplicity into complexity, darkness into light, chaos into order. From their fire came the chemistry of life, the architecture of galaxies, and the possibility of thought. They were the bridges between matter and meaning. Their legacy is not just light, it is everything that ever existed. They are the artisans of the cosmos, and their work endures in every breath, every idea, every world. They turn nothing into something. Before the stars, there was only hydrogen, plain, invisible, without form. From that simplicity, the stars built everything. Oxygen for oceans, carbon for life, iron for worlds. They took the raw material of existence and gave it structure, color, purpose. Through their heat and gravity, they shaped the void into beauty. To say that the stars created something from nothing is not poetry. It is physics. They are the universe's greatest act of imagination, the first sculptors of form in a sea of potential. They turned darkness into gold. The elements we treasure, the metals, the minerals, the foundations of technology and art, were born in the densest, darkest places. Gold and silver, platinum and uranium, all formed in the death throes of stars. Out of destruction came richness. Out of darkness came color. The universe, through its most violent acts, learned to make beauty. Every gleam of gold is a fossilized flash of light from a dying sun, proof that creation and destruction are one and the same melody, played in different keys. They turned silence into song. Before there were stars, there was no sound, no light, no story, only stillness. Then, from that quiet, came the hum of fusion, the resonance of atoms, the harmony of starlight filling the dark. The universe began to sing. That music continues in every photon, every ripple of energy. Across the void, it is the song of transformation, matter learning to shine, silence learning to speak. When we listen to the stars, even with our eyes, we are hearing that ancient symphony, the hymn of existence itself. They were, and are, the engines of creation. From the first star to the last, they have carried the same purpose, to turn potential into presence, to keep the universe alive with light. They gave birth to everything that has ever been, and even when they fade, their echoes remain. The stars are not gone. They are within us, around us, and beyond us, still shaping reality with the atoms they once forged. They were the engines of creation, and through their legacy, the universe still burns, still dreams, still becomes. The stars have spoken their story. From the first sparks in the darkness, to the last red embers at the edge of time, we have drifted through their lives, their births, their burnings, their endings, and the quiet gifts they leave behind. Every element in our bodies, every breath and heartbeat, was once light inside a distant sun. When we look up at the night sky, we are not reaching outward. We are remembering inward. For billions of years, the universe has turned emptiness into meaning, fire into form, light into life. And even now, as creation slows, its echo continues, softly, patiently, in the atoms of your hands, in the warmth that touches your skin, in the gentle pulse of your own existence. The stars are not gone. They shine through you. They think through you. You are the continuation of their fire, a fleeting, conscious moment in the long story of light. So as you rest tonight, let the mind settle into that vastness. Let the quiet around you feel like space itself, endless, calm, protective. Breathe with the rhythm of the cosmos, the same rhythm that has carried galaxies and held suns for billions of years. Now holds you too. The night does not end. It only changes color. And even when the stars grow cold, their story continues. In memory, in matter, in you. Sleep deeply, knowing that somewhere, light is still being born. And though it may take billions of years to arrive, it is already on its way. Good night, traveler of starlight. May your dreams drift through quiet galaxies, where creation never truly ends.